Look up at the night sky, just for a moment. Those pinpricks of light aren't just stars, they're fragments of an ancient story. A cosmic puzzle we've been trying to solve since the dawn of human curiosity. What if I told you that every shimmering dot out there holds a clue to the greatest mystery of all, where we came from, and why any of this exists at all? This isn't just about astronomy or physics. It's about the debates that crack open the very foundation of reality, the arguments that force us to question everything we thought we knew. From the explosive birth of the universe in the Big Bang to the mind-bending possibility of parallel worlds, the theories we'll explore today don't just describe space, they redefine what it means to exist. Think about the last time you felt truly small under that vast expanse of stars. That humbling sensation is just the beginning, because when cosmologists and philosophers clash over these ideas, they're not just trading equations, they're wrestling with questions that echo through human history. What came before time? Is our universe just one bubble in an infinite cosmic foam? Could there be versions of reality where the laws of physics are completely different? These aren't abstract thought experiments. The answers shape how we understand our place in the cosmos, why life emerged at all, and whether the universe has a purpose, or if it's all just spectacular, random chance. That's why this journey matters. Over the next 42 debates, we'll walk the razor's edge between science and philosophy, where hard data meets wild speculation, where the known universe collides with the unimaginable. Some of these ideas will feel like stepping into a sci-fi novel. Others might send shivers down your spine as you realize how much we still don't know. But one thing's certain, by the end, you won't look at the night sky the same way again. So let's begin where all great cosmic stories start, not with a single point in space, but with a question that has no easy answer. How does something come from nothing? The Big Bang Theory feels like the ultimate origin story, a single, cataclysmic moment where space, time, and matter burst into existence. But what if that story is incomplete? Picture this: the cosmic microwave background, that faint afterglow of the early universe, shows strange patches and asymmetries that don't quite fit the standard model. It's like finding fingerprints on a crime scene that don't match the suspect. Physicist Roger Penrose points to these anomalies as possible evidence of something older, a universe that existed before ours, leaving faint echoes in the data. Then there's the idea of a cyclical cosmos, where universes expand, contract, and explode anew in an endless loop. Imagine a cosmic heartbeat, each pulse birthing a new reality. This isn't just poetic speculation. Equations in string theory and quantum gravity suggest these models could be mathematically plausible. So why does it matter? Because if the Big Bang wasn't the true beginning, everything we think we know about time, causality, and even the nature of existence gets flipped on its head. Time might not be a straight arrow but a spinning wheel, and our universe could be just one page in an infinite cosmic library. The debate isn't just about revising textbooks, it's about whether we've been missing the prologue all along. But here's the twist: what if nothing isn't what we think it is? When we picture nothingness, we imagine pure emptiness, a void where not even space or time exists. Yet quantum physics paints a wildly different picture. Even in what we'd call a vacuum, particles flicker in and out of existence like cosmic fireflies, borrowing energy from the future to briefly take shape before vanishing again. This isn't poetic metaphor, it's measurable, a phenomenon called quantum fluctuation. So if nothing is actually a seething, unstable sea of potential, can we truly say the universe came from nothing at all? Philosophers have wrestled with this for centuries. David Hume famously argued that the very concept of absolute nothingness might be incoherent, a gap our minds can't truly bridge. Fast forward to modern cosmology, and his skepticism takes on new weight. Quantum field theory suggests that what we call empty space is anything but empty. It's a dynamic arena where virtual particles dance at the edge of reality, where energy fields vibrate with latent possibility. In this light, the Big Bang might not have been a sudden leap from nothing to something, but rather a shift, a phase transition in an eternal quantum substrate. That raises an even deeper question. If nothing is unstable, bubbling with unmanifest potential, does the universe's origin story need a creator, or was it inevitable? Some theories propose that universes could arise spontaneously from this quantum foam, like bubbles forming in a boiling pot. No divine spark, no external trigger, just the inherent instability of nothingness birthing everything. But this doesn't simplify the mystery, it reframes it. Now we're left wondering why the quantum vacuum has these properties in the first place. Why does nothing obey laws that allow something to emerge? This debate doesn't just challenge our scientific models, it forces us to confront the limits of language itself. When we say nothing, we're using a human concept to describe a reality that might be fundamentally alien to our intuition. The boundary between physics and metaphysics blurs here, where equations edge into philosophy, where the tools of science strain against questions about ultimate origins. Perhaps the real revelation isn't how the universe began, but how much stranger and more wondrous the answer might be than we ever imagined. Now let's peel back another layer of cosmic mystery. What if the universe we experience isn't truly three-dimensional at all? Imagine holding a credit card hologram where a flat surface projects a shimmering, seemingly solid image. The holographic principle suggests our reality might work the same way, an intricate illusion with all the information needed to construct our three-dimensional world actually encoded on a distant two-dimensional boundary. This isn't science fiction, it's a serious hypothesis born from the study of black holes. When physicists realized that the information swallowed by a black hole isn't lost but somehow preserved on its event horizon, the point of no return, it sparked a revolutionary idea. If a black hole's contents can be entirely described by data on its surface, could the same logic apply to the entire universe? Think of it like a cosmic projector screen, where every star, planet, and even your own thoughts might just be shadows cast from a flat, distant surface we can't perceive. Supporters of this theory point to tantalizing clues. Measurements of cosmic microwave background radiation, the oldest light in the universe, show unexpected pixel-like patterns, almost as if space itself has a fundamental resolution limit, like a digital display. Then there's the way quantum entanglement defies classical physics, with particles instantly influencing each other across vast distances. Could this be evidence of a deeper, interconnected code written on the universe's hidden boundary? But skeptics push back hard. If reality is a hologram, where's the projector? Why can't we detect the two-dimensional surface where everything is encoded? Critics argue that without direct experimental proof, like measuring a fundamental graininess in space-time, the idea remains speculative. Yet, even if unproven, the holographic principle forces us to rethink reality in radical ways. It suggests that space isn't an empty stage but an emergent property, like the illusion of depth in a painting. This debate isn't just about physics, it's about perception. If the holographic principle holds, then free will, consciousness, and even time might be secondary phenomena, side effects of a deeper computational process. Are we active participants in the universe, or just intricate patterns flickering on the surface of something far stranger? the answer could redefine not just cosmology, but what it means to be real. Dark energy might be the most unsettling discovery in modern cosmology, not just because we don't understand it, but because it's actively reshaping the fate of everything. Picture the universe as a loaf of raisin bread baking in an oven with galaxies as the raisins. For decades, we thought the expansion from the Big Bang was slowing down, like a loaf cooling after baking. Then, in the late 1990s, astronomers made a jaw-dropping observation. The bread isn't just expanding, it's rising faster and faster, as if some invisible hand cranked up the heat. That mysterious force, dark energy, it makes up roughly 68% of the cosmos, and we have no idea what it actually is. This isn't just academic curiosity. If dark energy keeps accelerating expansion, it could lead to a big rip, a catastrophic end where galaxies, stars, even atoms are torn apart. Imagine the fabric of space itself stretching until every bond holding matter together snaps. But here's where it gets stranger. Some theorists argue dark energy might not be constant. Enter quintessence, a dynamic version that changes over time, like a cosmic dial being tweaked. Could it grow weaker, avoiding a rip, or stronger, hastening the end? Nobel laureate Adam Rees, who helped discover dark energy, calls it the biggest head-scratcher in physics. Because if dark energy evolves, the universe's expiration date isn't just unknown, it's negotiable. Yet the real puzzle runs deeper. Why does dark energy exist at all? Einstein's cosmological constant, a mathematical fudge factor he later called his biggest blunder, turns out to describe dark energy eerily well. But the calculated value is off by a factor of 10 to the power of 120. That's like predicting a snowball's weight and getting an answer heavier than the observable universe. This isn't just a gap in knowledge, it's a screaming void, suggesting our theories are missing something fundamental. Alternative ideas abound. Maybe dark energy isn't a force but a symptom, a shadow cast by parallel universes tugging on ours through higher dimensions. Or perhaps space itself has an inherent energy we're only glimpsing indirectly. The stakes couldn't be higher. If dark energy's nature shifts even slightly, it could mean the difference between a universe that expands gently forever and one that shreds itself to oblivion. This debate isn't just about distant galaxies, it's about whether reality itself has an expiration date. What if every choice you've ever made spawned an entirely new universe? The idea isn't just a sci-fi trope, it's a serious scientific proposal. Imagine tossing a coin. Heads, you take a job offer. Tails, you decline. Quantum mechanics suggests both outcomes might happen, splitting reality into two timelines where each version of you lives a different future. This is the many worlds interpretation, where every quantum event branches the cosmos like an infinite tree. Proponents argue it solves quantum paradoxes, no collapsing probabilities, just every possibility playing out somewhere. But here's the catch: if these parallel worlds exist, why can't we detect them? Critics pounce on that very point. Without observable evidence, they argue, multiverse theories veer into philosophy. Renowned physicist Paul Steinhardt compares them to telling stories about invisible dragons. Yet supporters counter with quantum decoherence, the process that hides parallel realities from our view. Think of it like tuning a radio. Our universe is one station, while others broadcast on frequencies we can't access. Some even suggest cosmic inflation, the rapid expansion after the Big Bang, could have created bubble universes with different physical laws. Picture a frothing ocean of spacetime, each bubble a self-contained cosmos where gravity might be stronger, light slower, or life impossible. The implications rattle our sense of identity. If countless versions of you exist across the multiverse, some richer, some lonelier, some never born, does your life's path lose meaning? Philosopher Nick Bostrom proposes a chilling twist. Statistically, most conscious beings would exist in simulations run by advanced civilizations. Are we the originals or just one thread in a simulated tapestry? This debate forces us to confront the limits of science itself. Can a theory be valid if it's mathematically elegant but fundamentally untestable? Nobel laureate David Gross dismisses multiverses as a dangerous retreat from empiricism, while others, like Max Tegmark, champion them as inevitable extensions of quantum and inflationary models. The tension isn't just about parallel worlds, it's about how far we're willing to let math guide us beyond the edges of observation. Perhaps the most haunting question isn't whether multiverses exist, but what their existence would say about free will. If every decision spawns new timelines, are you truly choosing, or just riding a wave of quantum inevitability? The answer might lie not in telescopes, but in the mirror, because if parallel selves are out there, the most unsettling version of you could be the one reading this right now, wondering if it was ever really a choice. We've all felt time's grip, the relentless march of seconds, the unshakable arrow from past to future. But what if that flow is just a trick of the mind, a stubborn illusion woven into our perception? Quantum gravity, the quest to unite Einstein's relativity with quantum mechanics, paints a startling picture. At the deepest levels of reality, time might not exist at all. Think of it like watching a movie. We experience the story unfolding moment by moment, but the entire film already exists on the real, past, present, and future all equally real. Some physicists argue the universe works the same way, with time emerging from something more fundamental, like temperature arising from the motion of atoms. This idea turns causality on its head. If time isn't a bedrock feature of reality, then the very concept of a beginning for the cosmos becomes slippery. No creation moment, just a static block where every event from the Big Bang to the distant future exists simultaneously. Philosopher Julian Barber takes this further, suggesting that what we call time is just a sequence of snapshots, like frames in a film strip, with our brains stitching them into a flowing narrative. But here's where it gets thorny. If time isn't fundamental, why does it feel so real? Why do we remember the past but not the future? Neuroscientists point to our brain's predictive wiring. We're built to construct causality, to weave chaos into stories with beginnings and ends. Even physics hints at this divide. The second law of thermodynamics, with its irreversible rise of entropy, gives time its apparent direction. Yet in quantum equations, time often behaves like just another dimension, no more special than length or width. The implications ripple outward. If time is emergent, then free will becomes a puzzle. Are choices genuine or just predetermined points in a frozen cosmic tapestry? Religious and scientific origin stories alike hinge on linear time. But what if the universe has no true starting point, just an eternal geometry we're decoding one slice at a time? The debate isn't just academic. It challenges whether history, memory, even our sense of self are fundamental or elaborate side effects of deeper physics. Skeptics push back hard. If time isn't real, why do clocks measure it so precisely? Why does radioactive decay tick like a metronome across the universe? Defenders of emergent time counter that clocks measure change, not time itself, like using a speedometer to track motion without proving the road beneath you exists. Meanwhile, loop quantum gravity proposes that space and time are granular, pixelating into tiny quanta at the Planck scale, further blurring time's continuity. Perhaps the most profound question isn't whether time is real, but why evolution gave us such a compelling illusion. If our brains evolved to navigate a world of cause and effect, maybe time's flow is less a feature of the cosmos and more a tool for survival, a user interface overlaying a far stranger reality. After all, fish don't perceive water. Do we fail to perceive timelessness because we're swimming in its depths? This debate doesn't just reshape cosmology. It asks whether the ticking clock in your chest is measuring something real or just telling a story your mind can't help but believe. What if the world around you, the trees, the stars, even the device you're using right now isn't real? Not in the way we think, anyway. Oxford philosopher Nick Bostrom's simulation argument doesn't just flirt with this idea, it lays out a chillingly logical case. Imagine a future civilization with computing power so vast, they could create virtual worlds indistinguishable from reality. Now ask yourself, if such simulations outnumber the one base reality, what are the odds we're living in the original? The math is unsettling. Bostrom's trilemma presents three options. Either intelligent species go extinct before reaching this technological stage. They choose not to run ancestor simulations, or we're almost certainly living inside one. But this isn't just philosophical musing. Physicists are actively hunting for glitches in the matrix. If our universe is a simulation, there might be energy limits at the smallest scales, like pixels in a digital display. Some researchers analyze cosmic rays for signs of these limits, searching for unexpected drops in high-energy particles, evidence the universe has a resolution. Others propose quantum entanglement. Spooky action at a distance could be a processing shortcut, like a video game rendering only what the player sees. Even the way particles behave when unobserved, collapsing from probability, waves into definite states, echoes how a simulation might optimize resources, calculating details only when needed. Yet skeptics push back hard. If we're in a simulation, where's the evidence of computational constraints? Why no cosmic lag or memory leaks? Nobel laureate Frank Wilczek argues that the universe's mathematical elegance suggests it's the real deal, not a construct. But simulation theorists counter. A sufficiently advanced civilization could engineer a universe so seamless, its inhabitants would never suspect the truth. The implications ripple far beyond physics. If we're simulations, do our choices matter? Is pain just code? Some argue it changes nothing. Our experiences feel real to us, so they're real in the only way that counts. Others see a moral imperative. If we're someone's experiment, shouldn't we strive to make the simulation worth keeping? This debate doesn't just blur science and philosophy, it forces us to confront what reality even means. After all, if a simulated apple tastes sweet, nourishes you, and decays predictably, is it any less an apple? The answer might reshape not just cosmology, but our very sense of purpose in the cosmos. What if the seeds of life didn't sprout here on Earth at all, but rained down from the cosmos? Picture a comet, a frozen time capsule hurtling through space, carrying within it the molecular building blocks of life. When it crashes into a young planet, those ingredients spill into warm tidal pools, sparking the chain reaction that leads to microbes, plants, animals, and eventually you. This is Panspermia, the idea that life's raw materials, or even living organisms themselves, could have hitchhiked across the galaxy. The theory isn't new. Philosopher Anaxagoras floated it in ancient Greece, but modern science has given it startling credibility. Take the Murchison meteorite, a space rock that fell in Australia in 1969. Inside, scientists found amino acids, the very molecules that form proteins in every living cell. Even more intriguing, some of those amino acids had structures unlike anything produced by Earth's chemistry. Then there's the discovery of extremophiles, microbes thriving in Earth's harshest environments, from boiling vents to radioactive waste. If life can endure such extremes here, why not in the frozen void between stars? Experiments on the International Space Station have shown bacteria surviving years exposed to cosmic radiation, bolstering the case that life might be spacefaring. But skeptics raise a sharp objection. Where's the smoking gun? No one has yet found a microbe of unequivocally extraterrestrial origin. Critics argue that while Panspermia explains how life might spread, it dodges the deeper question of how life began in the first place, just kicking the can into interstellar space. Others point out that Earth itself had plenty of time and the right conditions for life to emerge independently. The famous Miller-Urey experiment in the 1950s showed that lightning in Earth's early atmosphere could generate amino acids from simple chemicals. So why invoke comets at all? The debate takes a philosophical turn when we ask, if life isn't unique to Earth, does that strip our existence of specialness or make the universe feel more alive? Some see Panspermia as humbling, reducing life to a cosmic accident. Others find it exhilarating, hinting at a galaxy teeming with biodiversity. Astrobiologist Chandra Wickramasinghe, a vocal Panspermia advocate, argues that if life permeates the universe, then intelligence might too, making humanity less a miracle and more part of a grand, interconnected web. Yet the implications get stranger. If life hops between worlds, could evolution itself be a shared cosmic process? Imagine DNA as a universal language, with planets exchanging genetic dialects via meteorite. This isn't pure speculation. Some scientists propose that the complex molecules in interstellar dust clouds could act as templates, seeding similar life forms across star systems. The idea blurs the line between biology and astronomy, suggesting that the story of life isn't just written in cells, but in the swirling chemistry of nebulas and the icy hearts of comets. The biggest question Panspermia raises isn't about proof, but perspective. If life is a traveler, not a local, then every world becomes a potential incubator or a waystation. Mars, Europa, even exoplanets light years away might host descendants of the same primordial spark. This shifts how we search for alien life. Instead of hunting for independent origins, we might be tracing a family tree scattered across the stars. Whether Panspermia is true or not, it forces us to see Earth not as an isolated cradle, but as one branch in a cosmic garden we've only begun to explore. Black holes aren't just cosmic vacuum cleaners, they might be the universe's most bizarre recycling centers. Picture this: a star collapses under its own gravity, crushing matter so densely that not even light can escape. But what happens to everything that falls in? For decades, physicists assumed it was gone forever, erased from existence. Then Stephen Hawking dropped a bombshell: black holes might not be eternal. They could slowly leak energy, evaporating over unimaginable eons through what we now call Hawking radiation. Here's the twist: that radiation appears random, like static noise. So where does all the information about the swallowed particles go? This is the black hole information paradox, and it sparked a war of ideas that could rewrite physics. One camp argues information is truly lost, violating quantum mechanics' core rule that information can't be destroyed. Others, like Leonard Susskind, propose holographic solutions, suggesting the data isn't gone but smeared onto the event horizon like cosmic graffiti, encoded in ways we don't yet understand. But the wildest theory: black holes might not be in points at all. Some models suggest the crushing singularity at their core could birth an entirely new universe, with our own cosmos possibly sprouting from one. Imagine a cosmic Russian nesting doll, where every black hole contains a fledgling reality with its own laws of physics. This isn't just about stellar corpses, it challenges our understanding of death itself. If matter isn't annihilated but transformed, does true annihilation exist? Philosopher Hilary Putnam once mused that identity might persist across radical changes, like a ship rebuilt plank by plank. Could black holes be the ultimate test of this idea? What falls into a black hole as a star might re-emerge as the Big Bang of another cosmos, its essence preserved in some unknowable way. Yet skeptics demand evidence. If black holes create universes, how would we ever observe it? The math might be elegant, but without empirical hooks, the theory risks drifting into metaphysics. Meanwhile, labs are simulating black hole conditions using supercooled atoms and lasers, hunting for clues in quantum echoes. The debate rages because it's not just about space, it's about existence. If black holes are cosmic alchemists turning destruction into creation, then even the void might hum with hidden potential. Consider the delicate balance of numbers that make our existence possible. If gravity were just slightly stronger, stars would burn out too quickly for life to evolve. If the electromagnetic force were even a fraction weaker, atoms couldn't bond. The universe's fundamental constants appear perfectly calibrated for life, like a lock with a billion possible combinations, yet somehow set precisely to the one that opens the door. This eerie precision is the heart of the fine-tuning argument, a puzzle that sparked one of the most heated debates in cosmology. Proponents of the anthropic principle argue there's no mystery here. We simply live in the rare universe where conditions allow observers like us to exist. It's like winning the cosmic lottery and marveling at the odds, ignoring that you couldn't complain if you hadn't won. But critics fire back. This is textbook selection bias. Imagine a puddle waking up and declaring the hole it fills must have been designed to fit its exact shape. The universe isn't fine-tuned for life. Life adapted to the universe's arbitrary rules. Yet the numbers keep haunting us. Take the cosmological constant, which governs the expansion of space. If it were slightly larger, galaxies couldn't form, slightly smaller, and the universe would collapse in on itself. The odds of it landing in the life-permitting range by chance. Astronomer Martin Rees compares it to throwing a dart blindfolded and hitting a bullseye the width of a single atom. Even atheist physicist Leonard Susskind admits the universe is damn strange. This is where theology tiptoes into the lab. Some see fine-tuning as evidence of a designer, not necessarily a religious one, but perhaps a cosmic architect tweaking the dials. Philosopher John Leslie offers the firing squad analogy. If 50 marksmen miss you, it's more plausible they intended to spare you than that they all coincidentally misfired. But multiverse theories offer a secular counter. If infinite universes exist with random constants, statistically, a few will hit the life-friendly jackpot by sheer probability. We just happen to be in one. The debate hinges on a deeper question. Is the universe's apparent fine-tuning a profound clue or a cosmic mirage? Quantum physicist Brandon Carter, who coined the term anthropic principle, cautions against conflating correlation with causation. Just because we observe a life-permitting universe doesn't mean it was engineered for us. It might simply be the only version where such observations are possible. Meanwhile, string theory posits a landscape of possible universes, each with different physical laws, making our existence less a miracle than an inevitability within an unfathomably vast ensemble. Skeptics aren't convinced. Physicist Paul Davies argues that multiverses merely kick the can down the road. What fine-tunes the laws that spawn these alternate realities? And if other universes are unobservable by definition, does invoking them cross from science into speculation? The tension here isn't just about equations. It's about how far we're willing to let curiosity stretch the boundaries of empiricism. Perhaps the most unsettling thought isn't whether the universe was designed for life, but what fine-tuning implies about reality's nature. If the constants weren't adjustable, if life were inevitable under any physical laws, we wouldn't be having this debate. The very fact that we notice the precision suggests something deeper, a universe that at least permits the question. Whether that's a fingerprint of intent or a quirk of probability, the answer would redefine not just our cosmic address, but our place in the grand story of existence. We think we understand the Big Bang as the ultimate starting gun, the moment when time itself flickered into existence. But what if that's just the beginning of the story? Quantum loop gravity, one of the most promising theories trying to unite relativity and quantum mechanics, paints a radically different picture. Instead of a singularity where time begins, it proposes a cosmic rebound, a bounce from a previous collapsing universe into our expanding one. Picture a slingshot pulled back to its limit, then suddenly releasing. Now imagine that slingshot is space-time itself. This idea shatters the intuitive notion of before and after. If time as we know it emerged from the Big Bang, how can we even speak meaningfully about what came before? Philosopher of physics Hugh Price likens it to asking what's north of the North Pole. The question might sound coherent, but the framework we're using breaks down entirely. Yet loop quantum gravity's equations suggest something astonishing. Time might not be fundamental at all, but rather an emergent property, like temperature arising from the motion of particles. In this view, the pre-Big Bang universe wasn't a void waiting in some temporal queue. It was a timeless quantum state, a roiling foam where cause and effect had no meaning. Supporters point to the cosmic microwave background for clues, those faint temperature fluctuations in the afterglow of the Big Bang. Some researchers argue they bear patterns statistically consistent with echoes from a prior cosmic phase, like finding fossilized ripples from a universe that came before ours. Then there's the problem of entropy. Our universe started in a state of improbably low entropy, a puzzle that makes more sense if it inherited order from a contracting predecessor, like a coiled spring storing energy for release. But critics aren't convinced. Without observable evidence of this pre-Big Bang era, they argue, the theory remains elegant mathematics rather than empirical science. Renowned physicist Sean Carroll counters that positing an eternal cycle of universes simply moves the mystery of origins elsewhere. What started the cycle? The debate crystallizes a deeper tension in cosmology. When our language and intuition are built on linear time, how do we conceptualize a reality where time isn't foundational? This isn't just about revising textbooks. If time is emergent, then our entire narrative of creation, from religious cosmogonies to scientific origin stories, might be projecting human-scale concepts onto a canvas far stranger than we imagined. The implications ripple into philosophy, theology, even the nature of causality itself. If the Big Bang wasn't a true beginning, but a transition from a timeless quantum realm, then the ultimate question shifts from how did time start? To why does time feel so inescapably real to us? The answer might lie not in telescopes, but in the wiring of our brain's evolution's way of making sense of a universe that operates on rules far beyond our everyday experience. We take for granted that we live in a world of 3 spatial dimensions: length, width, height plus time. But what if reality has hidden layers, folded up so tightly we can't perceive them? String theory, one of the most ambitious frameworks in physics, suggests exactly that: 6 or 7 extra dimensions curled into spaces smaller than an atom. Think of a garden hose seen from far away. It looks like a simple one-dimensional line, but up close, you discover it's actually a cylinder with a second dimension wrapped around its circumference. Now imagine that same principle applied to the fabric of space itself, with microscopic dimensions coiled at every point. This isn't just mathematical whimsy. These extra dimensions could solve one of physics' biggest puzzles: why gravity is so staggeringly weak compared to other fundamental forces. A magnet can lift a paperclip against Earth's entire gravitational pull. That's like a feather outweighing a battleship. If gravity's force leaks into these compact dimensions, it would explain why it appears diluted in our three-dimensional experience. Picture water seeping through a sponge. Most of it stays trapped inside, with only a trickle reaching the surface we can see. The hunt for these hidden dimensions isn't theoretical. Particle colliders like the Large Hadron Collider might create microscopic black holes, brief, vanishingly small signatures that could reveal gravity acting in higher dimensions. Other experiments search for deviations in the inverse square law of gravity at submillimeter scales, where extra dimensions might subtly alter how objects attract each other. Then there's the eerie phenomenon of quantum entanglement, where particles influence each other instantly across vast distances. Could this spooky action be evidence of particles connected through higher dimensional shortcuts, like ants crawling through the folded layers of a newspaper? Critics argue we're chasing phantoms. After decades, no experiment has conclusively detected extra dimensions. Nobel laureate Sheldon Glashow dismisses string theory as not even wrong, a beautiful idea untethered from testable predictions. Others counter that absence of evidence isn't evidence of absence. The scales involved might simply be beyond our current technological reach. The debate crystallizes a deeper tension in physics. When mathematics points compellingly toward unseen realities, how long should we keep looking before reconsidering our assumptions? Philosophically, hidden dimensions challenge our most basic intuitions. If higher dimensions exist, could consciousness itself be a higher dimensional phenomenon? Mystics have long spoken of unseen realms. Could ancient intuitions have glimpsed a truth that science is now quantifying? Or are we, like flatlanders trying to comprehend a cube, fundamentally limited by the dimensions we evolved to perceive? The answer might not just reshape physics, it could redefine what it means to experience reality at all. The most tantalizing possibility: these dimensions might not be static. Some models suggest they could unfurl under extreme conditions, like during the Big Bang or inside black holes. If so, our three-dimensional universe might be just one configuration of reality, a single page in a multidimensional atlas we've only begun to imagine. Whether they exist or not, hidden dimensions force us to confront an unsettling truth. The world we see may be the barest fraction of what's actually there. What if consciousness isn't something the universe has, but something the universe is? At first glance, the idea sounds like mystical speculation until you peer into the quantum realm, where particles seem to behave differently when observed. The double-slit experiment, one of physics' most famous puzzles, shows electrons acting as waves when unobserved but snapping into definite particles the moment we measure them. This isn't just a quirk of tiny objects. It suggests reality might respond to awareness in ways we're only beginning to comprehend. Panpsychism, the radical theory that consciousness is a fundamental property of matter, takes this even further. Imagine every electron, every quark, humming with a faint whisper of subjective experience, not thought or emotion as we know it, but a raw, primal form of awareness woven into the fabric of existence itself. Philosopher David Chalmers frames the hard problem of consciousness. Why does any physical process feel like something from the inside? Why aren't we all just unfeeling robots processing data? Traditional science struggles here, treating consciousness as a byproduct of brain chemistry. But panpsychists flip the script. What if consciousness came first and complex brains merely amplify it? Think of it like temperature. A single atom doesn't have warmth, but collective motion creates heat. Similarly, simple particles might possess proto-consciousness that compounds into rich inner lives in systems as intricate as human brains. Quantum mechanics adds fuel to this fire. The Copenhagen interpretation insists observation collapses quantum probabilities into definite outcomes, almost as if reality crystallizes under our gaze. Physicist John Wheeler took this further with his participatory universe hypothesis, proposing that observers are essential to bring the cosmos into being like a cosmic game of 20 questions where the answers don't exist until someone asks. Skeptics bristle at this, accusing panpsychism of smuggling metaphysics into physics. Neuroscientist Christoph Koch, once a vocal critic, now concedes that if consciousness emerges from integrated information, as his integrated information theory suggests, even rudimentary systems like photodiodes might harbor traces of it. The implications stagger the imagination. If consciousness is universal, then the boundary between self and world softens. A rock wouldn't think, but it might partake in the same underlying experiential fabric as your morning coffee or a blooming galaxy. This isn't just poetic thinking. Equations in quantum field theory treat observers as active participants, not passive spectators. The debate spills into ethics. If awareness permeates reality, does that change how we treat ecosystems, AI, or even particles in a lab? Yet critics demand harder proof. If electrons have inner experience, why no measurable signature? Philosopher Daniel Dennett dismisses panpsychism as fantasy physics, arguing that complexity, not fundamental awareness, explains consciousness. Others warn of the combination problem. How do countless micro-experiences merge into a unified mind? It's like asking how a trillion colorless pixels create a Technicolor movie. Defenders counter that Emergence solves similar puzzles. Water isn't wet at the molecular level, yet wetness appears when molecules collect. Perhaps the most unsettling question isn't whether particles have minds, but what that would say about our place in the cosmos. If observation shapes reality, are we co-creators of the universe simply by being here? The answer might lie not in labs or equations, but in the very act of questioning, because if consciousness is indeed fundamental, then the act of seeking to understand it could be the universe awakening to itself. Einstein called it spooky action at a distance, two particles separated by light years somehow mirroring each other's states instantaneously, as if space between them didn't exist. Quantum entanglement defies everything we know about locality. The idea that objects can only be influenced by their immediate surroundings. But what if this bizarre phenomenon isn't just a microscopic curiosity? What if entanglement scales up, weaving invisible threads between stars, galaxies, even across the entire cosmos? The implications would rewrite our understanding of reality itself. Picture two electrons born together in a lab, their spins linked in perfect opposition. Separate them by the width of the Milky Way, and measuring one still instantly sets the state of the other. No signal passing between them, no hidden mechanism we can detect. Now stretch that idea to cosmic proportions. Could entangled particles formed during the Big Bang still be whispering to each other across 14 billion years of expansion? Some cosmologists speculate that the large-scale structure of the universe, the vast cosmic web of galaxies, might bear the fingerprints of primordial entanglement, with distant clusters moving in suspicious synchrony. The math gets wilder. If entanglement pervades space, it might explain why the universe appears so uniform in all directions. The cosmic microwave background, that ancient afterglow from the universe's infancy, shows nearly identical temperatures everywhere, something hard to explain if distant regions never had time to thermally equilibrate. But if those regions were quantum mechanically linked in the early universe, their matching properties make eerie sense. It's like two ice cubes placed in separate rooms, somehow melting at the exact same rate without any connection unless, at some deeper level, they were never truly separate to begin with. Critics raise valid objections. For entanglement to span galactic distances, decoherence, the process that typically severs quantum links through environmental interference, would have to be miraculously avoided. Even a single stray photon can break entanglement, so how could delicate quantum states survive the violent chaos of the early cosmos? Some theorists propose a loophole, gravitationally mediated entanglement, where space-time itself acts as the silent carrier of quantum information. Just as gravity bends light, it might also preserve quantum correlations across vast reaches, hidden in the fabric of reality. This debate isn't just about physics, it's about ontology. If entanglement connects the cosmos, then the very notion of separate objects starts to crumble. Eastern philosophies have long spoken of universal oneness. Now, quantum mechanics might offer a mathematical framework for that intuition. Philosopher David Bohm's Implicate Order suggested that reality is a holographic projection of deeper, entangled layers, an idea that once seemed mystical but now finds echoes in cutting-edge cosmology. Yet the hardest question remains: if everything is interconnected, why does the world feel so fragmented? Why don't we experience this cosmic entanglement in daily life? The answer might lie in scale. Just as fish don't perceive the water they swim in, we may be too embedded in the quantum fabric to notice its stitches. Or perhaps entanglement's effects are subtle, manifesting only in the universe's grand architecture, not in our local reality. Experiments are pushing the boundaries. Teams are testing entanglement over increasing distances from labs to satellites, while others analyze galaxy surveys for statistical anomalies that might hint at cosmic-scale quantum links. The day we confirm entanglement spanning the universe would be revolutionary, not just for science but for how we see ourselves. No longer isolated observers, but active participants in a vast, whispering network where every measurement, every observation, might ripple across the cosmic web in ways we're only beginning to fathom. The most profound implication: if entanglement truly binds the cosmos, then the universe isn't just a collection of objects, but a single, dynamic entity, a cosmic symphony where every particle, every star plays its note in harmony with the whole. Whether this vision holds or collapses under scrutiny, one thing's certain: the answers won't just illuminate physics. They'll redefine what it means to be part of something vast beyond comprehension. For centuries, the idea that every effect must have a cause seemed as solid as the ground beneath our feet. But step into the quantum realm, and that certainty crumbles like a sandcastle in the tide. At scales smaller than a trillionth of a millimeter, particles pop into existence without any discernible cause, a phenomenon called vacuum fluctuation. This isn't theoretical speculation. We've measured it in labs. Electrons and positrons spontaneously appear from empty space, dance for unimaginably brief moments, then vanish again. If nature permits uncaused events at the smallest scales, why couldn't the universe itself be one such event? The implications rattle philosophy and theology alike. Aristotle's concept of an unmoved mover, a necessary first cause, has undergirded cosmological arguments for millennia. But quantum mechanics presents a stark alternative, a reality where causation isn't fundamental but emergent. Think of it like temperature. A single molecule doesn't have warmth. Heat arises from the collective motion of many particles. Similarly, causality as we experience it might be a large-scale illusion, emerging from countless quantum events that individually defy cause and effect. This turns the traditional "why is there something rather than nothing" question on its head. If causation isn't absolute, then the universe might not need a reason to exist at all. Yet critics push back hard. Just because quantum events appear uncaused at our current resolution doesn't mean they truly lack causation. Perhaps we just can't see the deeper mechanism. Nobel laureate Gerard T. Hooft compares it to watching a magician's trick. The rabbit seems to appear from nowhere, but there's a hidden method. Some interpretations of quantum mechanics, like pilot wave theory, restore strict determinism by positing hidden variables beneath the apparent randomness. Others argue that vacuum fluctuations aren't truly uncaused, but borrow energy from gravitational fields or spacetime itself, a kind of cosmic tab kept by the universe. The debate crystallizes around Planck scale physics, where space and time lose their familiar smoothness. Here, quantum foam bubbles with spacetime fluctuations so violent that before and after lose meaning. In this regime, asking what caused the universe might be like asking what's north of the North Pole, a category error. Physicist Sean Carroll argues that time itself may be emergent, making the very concept of a first moment misleading. Picture a pot of boiling water. Bubbles form spontaneously without a precise first bubble. Similarly, the universe could be one fluctuation in an eternal quantum sea, no more mysterious than foam on the ocean. Philosophers divide sharply on whether this voids the first cause argument. Atheists see it as proof the universe needs no creator, while theists counter that quantum mechanics merely describes how things happen, not why there's a framework for things to happen at all. Theologian William Lane Craig maintains that even if quantum events appear uncaused, they still operate within a finely tuned system of physical laws which itself demands explanation. This shifts the debate from what caused the Big Bang to what grounds the laws permitting spontaneous creation. The most profound implication isn't about origins but necessity. If the universe could exist without a cause, then existence itself might be a brute fact, not requiring justification, just being. This terrifies some and liberates others. Like realizing your childhood home was built on shifting tectonic plates, it forces us to confront that our deepest intuitions about reality might be provincial, shaped by scales too large to perceive the quantum foundations beneath. Whether the universe had a cause or not, the mere possibility it didn't stretches our imagination beyond comfortable limits into a cosmos where why might be the wrong question altogether. Stretching your imagination to its limits, try picturing a universe with no end, no walls, no boundaries, just an endless expanse of galaxies fading into the infinite. Now shrink that vision down to a self-contained cosmos, where if you traveled far enough in one direction, you'd loop back to where you started like an ant crawling on a globe. These aren't just thought experiments. They're real possibilities cosmologists grapple with when asking whether the universe is infinite or finite. The answer hinges on something deceptively simple: the shape of space itself. To understand how, imagine drawing a giant triangle across the cosmos. In a perfectly flat universe, the angles would add up to 180 degrees, just like in high school geometry. But if space has positive curvature like the surface of a sphere, those angles would bulge outward, summing to more than 180. Negative curvature, saddle-shaped, would pinch them inward. Satellite measurements of the cosmic microwave background, particularly the Planck mission, have scrutinized these angles with breathtaking precision. The result, space appears flat within a razor-thin margin of error, suggesting the universe could indeed stretch on forever. But here's the twist: a flat universe doesn't necessarily mean an infinite one. Topology introduces wild cards. Picture a video game where exiting the right side of the screen teleports you to the left, a finite space with no edges. Our cosmos might work the same way, curled into a hypertorus, a four-dimensional donut where every straight path eventually loops back. This wouldn't betray itself in local geometry. You'd need to spot repeating patterns in distant galaxy clusters or the cosmic microwave background, like a hall of mirrors on a universal scale. The implications dizzy the mind. An infinite universe guarantees that somewhere out there, an exact copy of you is reading these very words, thanks to the sheer probability of particles arranging identically given endless space. A finite one, though, raises unsettling questions. What lies beyond the boundary? Nothing, something. The very idea clashes with our intuition, as philosopher Immanuel Kant noted when he called the universe's infinitude an antinomy, a problem reason can't resolve. Critics of the infinite model point to the observable universe's startling uniformity. If space truly had no end, why wouldn't distant regions show more variation? Proponents counter that even infinity can have homogeneous patches, like an endless ocean with consistent chemistry. Meanwhile, advocates for a finite cosmos cite odd large-scale anomalies, like the mysterious cold spot in the cosmic microwave background, which some speculate could be a bruise from our universe colliding with another in a multiply-connected topology. The debate isn't just academic. If the universe is finite but unbounded, its total volume would dictate the scale of the largest possible structures. No galaxy cluster could grow larger than the circumference of space itself. An infinite cosmos, though, permits structures of limitless size with fractal patterns repeating ad infinitum. This isn't just about mapping the cosmos. It's about understanding whether reality itself has a size tag, or if, how big. Is a question without an answer. Perhaps the most humbling thought is this: we may never know for certain. Light from beyond a hypothetical loop might not have had time to reach us, or an infinite universe could forever hide its true nature beyond the horizon of observation. Like ants in a vast forest, we might only ever see trees, never the shape of the whole. Yet the search continues because whether finite or infinite, the answer defines not just the container of existence, but the very rules of what's possible within it. Einstein's equations once revealed a tantalizing possibility: bridges in the fabric of space-time connecting distant points like cosmic shortcuts. These wormholes, or Einstein-Rosen bridges, aren't just science fiction. The math allows them. Picture folding a piece of paper so two dots touch, then punching a pencil through. That's the essence of a wormhole, a tunnel through the warped geometry of the universe. But here's the catch. The same equations suggest these tunnels would snap shut the instant anything tried to pass, crushed by their own gravitational forces. That's where quantum physics enters the debate, whispering a radical idea. What if exotic matter with negative energy could prop them open? The concept isn't as far-fetched as it sounds. Quantum mechanics already allows for fleeting particles with negative energy, like the Casimir effect's phantom force between metal plates in a vacuum. Scale that up, and you might theoretically line a wormhole's throat with this exotic matter, counteracting the collapse. Physicist Kip Thorne explored this in the 1980s, calculating that such stabilization could mathematically, at least, make traversable wormholes possible. Imagine stepping into a portal on Earth and emerging near Proxima Centauri, all in the blink of an eye. The implications for interstellar travel are staggering. No generation ships, no cryogenic sleep, just a cosmic subway system linking the galaxy. But the obstacles loom large. First, no one knows how to produce or harness the quantities of exotic matter required. Second, even if you stabilized a wormhole, the tidal forces inside might shred anything attempting the journey. Picture falling into a gravitational whirlpool where space-time stretches you like taffy while crushing you sideways. Some models suggest rapid rotation could mitigate this, creating a safer corridor, but the engineering challenges border on fantasy. Then there's the causality problem. If you could traverse a wormhole fast enough, you might arrive before you left, violating causality and unleashing paradoxes like killing your own grandfather before your parent was born. The debate splits physicists. Optimists point to theoretical breakthroughs like quantum entanglement's non-local effects, hinting that space-time might be more flexible than we thought. Others, like Stephen Hawking, propose the chronology protection conjecture, a cosmic no to time travel, enforced by quantum mechanics preventing paradoxes. Wormholes might exist, but nature could have built in safeguards to keep them untraversable. Meanwhile, astronomers search for indirect evidence, like gravitational anomalies or gamma-ray signatures that might betray a wormhole's presence. Yet the most profound question isn't whether wormholes can exist, but what their possibility says about reality. If space-time can be punctured and stitched together, then the universe might be less like a rigid stage and more like a dynamic tapestry, full of hidden seams and folds waiting to be discovered. Whether they're traversable or not, wormholes remind us that the cosmos still holds mysteries bold enough to defy our boldest dreams. Every particle we know has a mysterious twin, an identical opposite carrying the same mass but inverted charge. Meet antimatter, nature's perfect mirror. When matter and antimatter collide, they annihilate in a flash of pure energy, leaving nothing behind. Here's the cosmic riddle. If the Big Bang produced equal amounts of both, why is our universe overwhelmingly made of matter? Where did all the antimatter go? This isn't just a missing pieces puzzle. It's a gaping hole in the story of existence itself. The standard model of particle physics assumes perfect symmetry between matter and antimatter at the universe's birth. Yet somehow, for every billion antimatter particles, 1,000,000,001 matter particles survived a tiny asymmetry that snowballed into everything we see today. Experiments at CERN Large Hadron Collider have caught glimpses of this imbalance. When studying decays of particles called B mesons, physicists observed antimatter versions decaying slightly differently than their matter counterparts, a violation of so-called CP symmetry. It's as if the universe has a hidden preference for matter, like a scale tilted by an invisible hand, but the plot thickens. What if entire regions of antimatter still lurk in the cosmos, segregated by vast voids? Some theories suggest antimatter galaxies could exist, shining with the light of anti-stars where anti-hydrogen fuses in anti-cores. The hitch: when such regions border matter-dominated space, their collisions would produce gamma-ray bursts detectable across the universe. Astronomers have scoured the skies for these annihilation fireworks and found nothing conclusive. The Alpha Magnetic Spectrometer on the International Space Station hunts for antihelium in cosmic rays, a smoking gun for distant antimatter domains. So far, silence. Critics argue this absence proves antimatter's near total disappearance. Supporters counter that segregation could be more extreme than we imagine, with antimatter hiding beyond our observable horizon. Meanwhile, alternative explanations emerge. Could antimatter have different gravitational behavior, sinking into cosmic voids we can't probe? Experiments like CERN Alpha Project now test whether anti-hydrogen falls up or down, a question that sounds like parody but could rewrite physics. The deepest implication isn't just about missing antimatter, it's about creation's fragility. That 1 part in a billion asymmetry wasn't a bug, it was the feature that allowed anything to exist at all. Tweak the numbers slightly, and the universe might have annihilated itself into pure radiation before stars could form. This fine-tuning echoes through cosmology, whispering that existence hangs by a thread. Perhaps antimatter's greatest lesson is humility. The universe didn't have to be this way. Its lopsidedness might hint at physics beyond our model's particles or forces yet undiscovered that tip the scales. Until we know, every atom in your body stands as evidence of a mystery written into the fabric of reality, a cosmos that, against all odds, chose to be something rather than nothing. We watch an egg shatter on the floor and instantly no time has moved forward. But what if the universe has a rewind button? At the quantum level, time doesn't seem to care which way it flows. Particles behave identically whether time runs forward or backward, like a movie that makes perfect sense played in reverse. This microscopic symmetry clashes violently with our everyday experience, where spilled milk never jumps back into the glass. The disconnect reveals a haunting possibility. The arrow of time might not be a fundamental feature of reality, but a quirk of perspective, one that could, in theory, flip. Consider the humble deck of cards, shuffle it thoroughly, and the ordered sequence gets randomized, a one-way street toward chaos, just like entropy increasing in the universe. But here's the twist: the laws governing each shuffle work perfectly fine in reverse. There's no mathematical reason the deck couldn't unshuffle itself through the exact same motions backward. The reason we never see it happen isn't because it's impossible, it's just staggeringly unlikely. Now scale that up to the cosmos. The Big Bang started the universe in a state of unimaginably low entropy, like a pristine deck fresh from the box. Every moment since has been a shuffle toward disorder. But given enough time, think trillions upon trillions of years, quantum fluctuations could theoretically conspire to reverse the process, stitching broken eggs back together and reassembling shattered stars. Physicists like Sean Carroll argue that in an eternally expanding universe, entropy might eventually stop increasing, creating conditions where time's arrow loses its direction. Picture a cup of coffee cooling to room temperature. The heat dissipates until equilibrium is reached, and the system forgets which way time should flow. On cosmic scales, this could mean a future where cause and effect blur, where the universe becomes a timeless sea of random fluctuations. Experiments with quantum particles already hint at this. In 2018, scientists at Moscow's Institute of Physics and Technology used a quantum computer to simulate time reversal, effectively making a particle unscatter as if rewinding a tape. Yet skeptics counter that these are controlled micro-experiments, not proof the cosmos could reset. The sheer scale of entropy reversal required boggles the mind, like every molecule in a dispersed gas cloud spontaneously coordinating to cram back into an open bottle. Nobel laureate Roger Penrose proposes a wild alternative, that the universe's eventual heat death might trigger a new Big Bang, not by reversing time but by resetting entropy through a process called conformal cyclic cosmology. In this view, the far future's cold, empty universe becomes mathematically indistinguishable from the hot, dense singularity of a new beginning, a cosmic Ouroboros where time loops without reversing. The debate forces us to confront what time even is. If microscopic physics is time symmetric, why does macroscopic time feel so irreversible? The answer might lie in emergence, the way collective behavior creates properties that individual components don't possess. A single water molecule isn't wet, but trillions together create wetness. Similarly, time's arrow could be an emergent property of countless particles moving statistically toward disorder. This doesn't just challenge physics, it rattles philosophy. If time can reverse, what happens to free will? Are choices just illusions waiting to be undone? The most startling implication isn't about the far future, it's about now. If time's flow isn't baked into reality's foundation, then our experience of past, present, and future might be a trick of the scale at which we exist. Like fish unaware of water, we're trapped in a perceptual frame where time feels absolute, while the universe whispers it's anything but. Whether that whisper grows into a shout or fades into the void depends on how deeply we dare to question the ticking of the cosmic clock. Tiny ripples in the newborn universe, smaller than an atom, quieter than a whisper, might hold the secret to everything we see around us today. Picture the cosmos moments after the Big Bang, a seething quantum foam where particles flicker in and out of existence, where energy fluctuates wildly even in what we'd call empty space. These quantum fluctuations, random as they seem, could have been the seeds from which galaxies, stars, and planets eventually grew. It's a staggering thought that the majestic spiral of Andromeda or the vast web of galaxy clusters might trace back to subatomic trembles in the fabric of reality itself. The evidence lies in the cosmic microwave background, that ancient afterglow from the universe's infancy. Satellite maps reveal faint temperature variations, hotter and cooler patches no larger than 1 part in 100,000. These imperfections match predictions from quantum mechanics, as if the microscopic jitters of the early universe were stretched to cosmic scales by inflation, the rapid expansion that followed the Big Bang. Gravity then amplified these tiny density differences over billions of years, pulling matter into the denser regions while emptying the voids. The result: the glittering tapestry of galaxies we observe today. But this raises a profound question. If cosmic structure emerged from quantum randomness, does that mean chaos is the true architect of order? At first glance, it defies intuition. We're used to thinking of randomness as disruptive, like static drowning out a radio signal. Yet here, noise becomes the blueprint. Some theorists argue this isn't just a cosmic fluke, but a fundamental feature of reality. In quantum physics, what we call empty space is anything but empty. It's a turbulent sea of virtual particles and fluctuating fields. Without this underlying chaos, the universe might have remained featureless, a smooth soup of particles with no galaxies, no stars, no planets. Critics push back, pointing to the fine-tuning required for these fluctuations to produce a life-friendly cosmos. The initial amplitude of those quantum ripples had to be just right, too weak, and matter would never clump into galaxies, too strong, and the universe would collapse into black holes before stars could form. This precision fuels debates about whether randomness alone can explain the universe's large-scale order, or if deeper principles guided the process. Some propose that quantum fluctuations themselves might not be purely random but influenced by hidden variables or higher dimensional physics we've yet to uncover. The philosophical implications run deep. If chaos births structure, what does that say about other seemingly orderly systems, life, consciousness, even society? Biologists see echoes in evolution, where random mutations drive the emergence of complexity. Economists spot parallels in market behaviors, where volatility spawns innovation. The universe might be teaching us that order and randomness aren't opposites but partners in an endless dance, with chaos not as the enemy of pattern but its unwitting collaborator. Yet the mystery lingers. Why does quantum noise translate so elegantly into cosmic architecture? Perhaps the answer lies in scale. What appears as randomness at the subatomic level smooths into statistical regularity when amplified across billions of light years, like individual raindrops blending into a steady downpour. Or maybe we're seeing the universe's version of spontaneous symmetry, breaking a phenomenon where uniform conditions give way to structured diversity, like a frozen lake cracking into intricate patterns under stress. The most humbling thought isn't that randomness built the cosmos, it's that without it, we wouldn't be here to wonder. Every atom in your body, every star in the sky, owes its existence to quantum tremors so slight they'd vanish in a heartbeat, yet so consequential they shape the fate of everything. Whether this makes the universe feel more miraculous or more mechanical depends on perspective, but one thing's certain: the line between chaos and order might be far thinner and far stranger than we ever imagined. Black holes devour everything in their path, but what if the universe has cosmic fountains spewing matter instead of swallowing it? Enter white holes, the hypothetical opposites of black holes predicted by the same equations that describe their dark twins. Imagine a black hole running in reverse. Instead of an event horizon where nothing escapes, a white hole would have a boundary where nothing can enter, violently ejecting matter and energy like a galactic geyser. The math allows it. Einstein's field equations are time-symmetric, meaning they don't care if events run forward or backward. Flip a black hole's collapse footage in reverse, and you've got a white hole's explosive birth. The question isn't just whether white holes exist, but where their material would come from. One provocative idea ties them directly to black holes, suggesting that what goes in must come out somewhere. Theoretical physicist Carlo Rovelli proposes that when quantum effects prevent a black hole from fully collapsing into a singularity, it might rebound as a white hole after billions of years. Picture a star collapsing into a black hole, then after a timescale dwarfing the current age of the universe, exploding back out as a white hole. The process would be agonizingly slow from our perspective, like watching paint dry on a cosmic scale, but it offers a tantalizing solution to the black hole information paradox. Matter isn't lost, just delayed. Yet the cosmos seems suspiciously devoid of these luminous eruptions. If white holes litter the universe, why haven't telescopes spotted them? Some theorists argue they'd be indistinguishable from short-lived, high-energy events like gamma-ray bursts, the universe's most violent explosions. Others speculate that white holes could only form in the early universe, their energy long since diluted by expansion. There's even a fringe hypothesis that the Big Bang itself was a primordial white hole, with all the universe's matter erupting from a singularity in reverse black hole fashion. Critics dismiss white holes as mathematical curiosities with no basis in observation. The second law of thermodynamics poses a steep hurdle. Entropy always increases, making the spontaneous reversal of a black hole's collapse seem fantastically improbable. Astrophysicist Sean Carroll compares it to expecting smoke to flow back into a cigarette. Even if quantum gravity permits white holes, the universe might conspire to prevent them, like a one-way valve enforcing cosmic order. But the debate isn't just about stellar mechanics, it challenges our understanding of time's arrow. If white holes are real, they'd be regions where causality flips, where the future influences the past. Philosophers ponder whether such objects would render the universe inherently unpredictable, with information leaking from tomorrow into today. Science fiction loves this idea, but physicists caution that any macroscopic white hole would likely destabilize instantly, its exotic matter evaporating in a burst of radiation. Perhaps the most intriguing twist comes from loop quantum gravity, which suggests white holes might not be separate objects at all, but the final phase of a black hole's life cycle, a cosmic butterfly emerging from a dark chrysalis. If true, every black hole could someday blossom into a radiant white hole, turning the universe's ultimate traps into engines of rebirth. Until we spot one, white holes remain a dazzling mirage at the edge of theory, reminders that the cosmos might still hold surprises wilder than fiction. Whether they're out there or not, they force us to question if the universe plays by rules we've only begun to glimpse. The universe isn't just expanding, it's doing so at a breakneck pace, as if some unseen hand pressed harder on the gas pedal. For decades, astronomers assumed gravity would eventually slow the cosmos's post-Big Bang growth, like a ball tossed upward, gradually losing speed. Then, in 1998, two teams studying distant supernova dropped a bombshell. The expansion isn't slowing down. It's accelerating, with galaxies fleeing from one another faster every second. The culprit, a mysterious force dubbed dark energy, making up nearly 70% of the universe's total energy budget. But here's what keeps cosmologists up at night. If this acceleration continues unchecked, the cosmic fabric itself could one day stretch too thin for galaxies, or even atoms, to hold together. Picture a rubber band being pulled from both ends. At first, it stretches smoothly but tug hard enough, and the material thins until it snaps. Now replace the rubber band with space-time and the hands with dark energy. This is the nightmare scenario called the Big Rip, where expansion outmuscles every fundamental force. First, galaxy clusters would tear apart as the space between them grows faster than gravity can compensate. Next, individual galaxies would unravel, stars drifting into the void like lonely ships. Eventually, planetary systems, then planets themselves, would rupture. In the final moments, even atomic nuclei would be shredded as the space between quarks expands faster than the strong nuclear force can bind them. The universe would end not with a whimper, but with a silent, invisible rending of reality's very fabric. Yet not all models spell doom. Some theorists argue dark energy might not be constant but dynamic, a field called quintessence that could weaken over time. Imagine a car's cruise control adjusting to traffic. If dark energy throttles down, expansion might stabilize, avoiding catastrophe. Others propose even wilder ideas, that dark energy is the signature of parallel universes in a higher dimensional bulk, their gravity subtly tugging ours apart. The problem, evidence remains frustratingly indirect. While the European Space Agency's Euclid telescope and the Dark Energy Survey scour the cosmos for clues, dark energy's true nature stays as elusive as ever. The stakes couldn't be higher. If expansion accelerates indefinitely, the universe faces a cold, lonely demise not in fire, but in ice. Distant galaxies will eventually vanish beyond an unreachable horizon, their light stretched into undetectable radio waves. Civilization's future descendants might gaze at an empty sky with no clue other islands of matter ever existed. This isn't just about far-off astrophysics, it's about whether the universe itself has an expiration date. And the clock is ticking not on human scales, but in cosmic terms, where billions of years pass like breaths. Skeptics counter that we might be misreading the data. Could supernova measurements be skewed by interstellar dust or unknown stellar physics? Some alternative theories, like modified Newtonian dynamics, tweak gravity itself to explain cosmic acceleration without invoking dark energy. Yet these alternatives struggle to match the precision of dark energy models, leaving most cosmologists convinced something strange is indeed pushing the universe apart. The most unsettling question isn't whether expansion will continue, but why it began accelerating when it did. For billions of years after the Big Bang, gravity-dominated galaxies formed, stars ignited. Then, roughly 5 billion years ago, dark energy took the wheel. This timing feels uncannily convenient for life. Had acceleration started earlier, matter wouldn't have clumped into galaxies. Later, and stars might not have formed at all. Is this coincidence a clue or just another roll of the cosmic dice? The answer could redefine not just our future, but our understanding of why the universe unfolds as it does. Whether dark energy is a constant force or a fleeting phase, its discovery reminds us that the cosmos is far stranger and more dynamic than we ever imagined. Einstein's cosmic speed limit, nothing can outrace light, seems unbreakable. Yet in its first trillionth of a second, the universe might have shattered that rule. Cosmic inflation, the theory that space underwent a hyper-fast expansion immediately after the Big Bang, suggests space-time itself ballooned faster than light could traverse it. Picture a rubber band stretching so rapidly that ants crawling across it couldn't keep up, except here, the ants are photons, and the rubber band is the fabric of reality. This isn't a violation of relativity, but a loophole. Einstein's law forbids objects within space from exceeding light speed, not space itself from stretching. Think of it like dots on an inflating balloon. As the surface expands, distant dots separate faster than any single dot could move, yet no dot breaks the rules. Inflation leverages this distinction, proposing that space didn't just grow but exploded outward at speeds making light seem sluggish. The numbers stagger the imagination. Regions smaller than an atom unfurled to the size of a grapefruit in fractions of a second, a growth rate that would leave light billions of years behind. Critics pounce on the paradox. If inflation outpaced causality, how could the universe maintain coherence? Shouldn't regions blown apart too quickly to exchange signals show wild variations? Yet the cosmic microwave background reveals eerie uniformity, as if distant areas were once neighbors. Inflationists counter that pre-inflation, the universe was tiny enough to equalize temperature before hyper-stretching locked it in. It's like baking a cake where ingredients perfectly mix before the oven's heat fixes their distribution. The debate heats up when we ask what powered this hyperdrive expansion. Quantum fields, theorists suggest specifically, an inflattened field whose energy briefly dominated the cosmos. As this field decayed, its energy reheated the universe, creating the hot soup of particles we recognize as the Big Bang's aftermath. But skeptics demand evidence beyond elegant math. Where's the smoking gun? Some point to gravitational waves, ripples in space-time from inflation's violent stretch that might imprint on the cosmic microwave background. Experiments like BICEP hunt for these fingerprints, though dust interference has muddied results. Alternative theories scramble to explain inflation's successes without superluminal speeds. Could a bouncing universe, cycling through contraction and expansion, achieve uniformity differently? Or might quantum entanglement's spooky connections have synchronized distant regions without requiring faster-than-light inflation? Each idea faces hurdles, leaving inflation as the reigning, if unproven, champion. The implications rewrite physics rulebook. If space can stretch faster than light, could warp drives, stretching spacetime around a ship sidestep light speed limits. NASA Eagleworks Lab probes this fringe idea, though practical engines remain speculative. More profoundly, inflation's superluminal sprint hints that light speed limit, like Newton's absolute time, might be a local law, not a cosmic absolute. Perhaps the boldest question isn't whether inflation happened, but what its breakneck expansion says about reality's plasticity. If spacetime can outpace light, what other intuitions about limits might crumble under closer scrutiny? The answer could reveal a universe far more dynamic and far stranger than Einstein ever dreamed. Quantum physics shatters our everyday notions of reality, not just in the lab, but at the very foundations of existence. At the subatomic level, particles exist in ghostly superpositions, hovering between all possible states until measured. This wave function collapse, where probabilities crystallize into definite outcomes upon observation, raises a staggering question. If consciousness plays a role in shaping reality at the smallest scales, could it have been the spark that ignited the cosmos? The idea that mind might sit at creation's center isn't mysticism, it's a frontier where quantum theory brushes against cosmology's deepest mysteries. Consider the double-slit experiment, physics' most famous demonstration of quantum weirdness. When unobserved, electrons behave as waves, creating interference patterns. The moment a detector clicks, they snap into particle-like behavior. This observer effect suggests measurement itself alters reality, a phenomenon that led physicist John Wheeler to propose the participatory universe. where observers are cosmic co-creators. Extend this logic to the Big Bang, and you arrive at a radical possibility. The universe may have needed a primordial observer to transition from quantum potentiality to concrete existence. It's as if the cosmos was waiting in a superposition of possible states until some form of proto-consciousness looked and collapsed the wave function of reality itself. Proponents like physicist Amit Goswami argue this resolves the fine-tuning problem. Instead of invoking multiverses or divine designers, consciousness becomes the selective mechanism, a universe aware of itself from the first instant. In this view, the Big Bang wasn't just a physical event but a perceptual one, like a dreamer waking into their own dream. The math finds surprising support in quantum gravity theories, where spacetime's emergence resembles wave function collapse. Loop quantum cosmology, for instance, describes the early universe as a fuzzy quantum cloud that only crystallizes into classical spacetime through interaction, a process eerily mirroring how observation defines quantum states. Yet skeptics wield Occam's razor. Why posit cosmic consciousness when simpler explanations exist? Traditional quantum mechanics treats observers as any physical system that records information, not necessarily conscious beings. A photon hitting a camera sensor collapses wave functions without human involvement. Critics like Sean Carroll argue that invoking consciousness as a causal force is unnecessary. Quantum decoherence, where environmental interactions destroy superpositions, explains wave function collapse without mystical additives. The cosmic microwave background's uniformity also poses a challenge. If reality requires observers, how did the early universe achieve such coherence before stars or life emerged? The debate spills into philosophy's oldest territory, the mind-matter relationship. Idealists have long argued reality is mental construct, while materialists see mind as a latecomer in a pre-existing physical world. Quantum consciousness theories split the difference, suggesting mind and matter co-evolved, a dance where observation and existence bootstrap each other into being. Some models even speculate that the universe's initial low entropy, which gives time its arrow, reflects a primordial act of quantum observation, like a cosmic version of Schrödinger's cat deciding to be alive. Experiments remain elusive but not impossible. If consciousness alters quantum systems, then human intention might, in principle, influence delicate lab setups. The controversial Global Consciousness Project claims to detect such effects during worldwide emotional events, though mainstream science remains unconvinced. More credibly, experiments in quantum biology explore whether photosynthesis or bird migration harnesses quantum coherence, hinting that nature might exploit observer effects long before human minds evolved to ponder them. The most profound implication isn't about origins but meaning. If consciousness helped birth the cosmos, then the universe isn't just a machine, it's a story being written by its own characters. This flips the Copernican revolution inward. Instead of being insignificant specks, observers become essential actors in reality's unfolding drama. Whether the evidence ultimately supports this view or not, the mere possibility reminds us that quantum strangeness isn't confined to tiny particles. It might echo through the grandest scales of existence, binding mind and cosmos in ways we've only begun to imagine. Imagine a universe governed by two sets of rules that refuse to speak the same language. On cosmic scales, Einstein's general relativity choreographs the graceful dance of galaxies and black holes. In the subatomic realm, quantum mechanics orchestrates the chaotic buzz of particles flickering in and out of existence. For over a century, these theories have reigned supreme, yet they clash violently when forced to interact. The quest for a theory of everything isn't just about tidying up physics. It's about discovering whether reality has a single set of rules, or if we've been staring at disconnected fragments of a puzzle too vast to comprehend. String theory once seemed the frontrunner in this grand unification. Picture the universe's fundamental building blocks not as dots, but as vibrating strings so tiny that if an atom were the size of our solar system, a string would be no larger than a tree on Earth. These strings' vibrations would dictate all forces and particles, weaving gravity and quantum behavior into a single mathematical tapestry. The elegance is undeniable until you peek behind the curtain. To make the equations work, string theory demands 10 or 11 dimensions, a menagerie of undiscovered particles, and a landscape of possible universes so vast it makes the multiverse seem claustrophobic. Nobel laureate Sheldon Glashow likens it to a theory of anything, so flexible it could explain everything, yet predict nothing testable. But string theory isn't the only contender. Loop quantum gravity takes a starkly different approach, proposing that space itself is woven from finite, interlocking loops, a fabric not smooth but pixelated. Think of spacetime as a mesh of microscopic rings, where gravity emerges from their quantum interactions. This framework beautifully avoids singularities, those pesky infinite densities in black holes, but struggles to incorporate other fundamental forces. Meanwhile, lesser-known approaches like causal dynamical triangulations simulate spacetime as a mosaic of tiny geometric shapes, evolving step by step like a cosmic board game. The stakes transcend academic squabbles. A true theory of everything wouldn't just reconcile relativity and quantum mechanics, it would redefine our understanding of existence. Consider black holes again. Relativity says their cores crush matter into oblivion. Quantum theory insists information can't be destroyed. A unified framework might reveal black holes as cosmic transformers, not destroyers, gateways to new physics where space-time reorganizes itself. Similarly, the Big Bang's singularity vanishes in some quantum gravity models, replaced by a quantum bounce from a prior universe. Suddenly, the moment of creation isn't a dead end, but a bridge. Yet skeptics whisper a heretical thought. What if no theory of everything exists? The universe might operate with layered rules, like a video game where different physics engines handle planets versus particles. After all, we don't expect Shakespearean sonnets to explain photosynthesis. Why should one theory govern all scales? Even Einstein suspected deeper truths might remain forever beyond our grasp. The most tantalizing possibility isn't that we'll find a final equation, but that the search itself will unveil questions we've not yet learned to ask. Like explorers mapping a coastline only to discover it stretches endlessly, we might find that every answer unravels new mysteries. Whether the theory of everything is a destination or a mirage, the journey reshapes how we see reality, not as a clockwork mechanism, but as a living, breathing puzzle inviting us to look deeper. They slip through your body by the trillions every second, silent and unnoticed neutrinos, the universe's most elusive particles, born in the hearts of stars, supernova, and even Earth's own radioactive decay. These ghostly travelers barely interact with matter at all. A neutrino could pass through a light year of lead without a single collision. Yet despite their ethereal nature, neutrinos might hold one of cosmology's heaviest secrets. Could they be the dark matter we've been searching for all along? For decades, dark matter's identity has been physics' ultimate cold case. We see its gravitational fingerprints, galaxies spinning too fast to hold together, light bending around invisible mass, but the culprit remains at large. Most theories point to hypothetical particles like WIMP, weakly interacting massive particles, yet detectors buried deep underground have come up empty after years of hunting. Enter neutrinos. We know they exist. They're notoriously hard to detect, and they outnumber atoms in the universe by 1,000,000,000 to 1. If even a fraction of them have enough mass, their cumulative gravity could explain dark matter's pull. The math gets intriguing. Neutrinos were long thought to be massless until experiments in the late 1990s caught them shape-shifting between three types: electron, muon, and tau neutrinos, a trick only possible if they have some mass. But how much? Current estimates suggest each neutrino weighs less than 1/1,000,000th of an electron, seemingly too slight to matter. Yet scale that up to the countless neutrinos flooding the cosmos, and their collective heft becomes staggering. Some models propose sterile neutrinos, a hypothetical fourth type far heavier than their known cousins, lurking just beyond our detection. These could be dark matter's dark horse, invisible, abundant, and massive enough to bend spacetime without lighting up our detectors. Critics pounce on two glaring holes. First, neutrinos move at near light speed, earning them the label hot dark matter. Simulations show such fast-moving particles would smear out galaxy clusters, preventing the delicate cosmic web we observe. Cold dark matter, in contrast, moves sluggishly, allowing structures to clump. Second, the cosmic microwave background's precise patterns suggest dark matter must be collisionless, barely interacting even with itself. Neutrinos fit this bill, but their confirmed masses are orders of magnitude too small to match observations. The debate isn't just about particle physics, it's a tug of war between elegance and evidence. Neutrinos as dark matter offer a tantalizing economy. No new particles need inventing, just a tweak to known physics. Yet the universe seems to demand something heavier and slower. Experiments like the upcoming Deep Underground Neutrino Experiment, DUNE, aim to settle the score, probing neutrino masses and hunting for sterile varieties. Meanwhile, astrophysicists scour dwarf galaxies, where dark matter's signal is strongest, for anomalies that might betray neutrino influence. Perhaps the most radical idea isn't that neutrinos are dark matter, but that they're part of a larger shadow ecosystem. Alongside other exotic particles, they might contribute to the missing mass without dominating it, a cosmic choir where no single voice carries the melody. This would mean dark matter isn't one thing, but many, a hidden menagerie of particles, each leaving faint gravitational traces. The implications ripple beyond astronomy. If neutrinos have enough mass to shape galaxies, then these barely their particles streaming through you right now are quietly steering the fate of the cosmos. Whether they solve dark matter's riddle or not, they remind us that the universe's most powerful forces often wear the lightest disguises. Imagine the universe as a frozen lake on the brink of spring, seemingly solid, stable, but secretly harboring a fragility beneath the surface. Now replace the ice with the quantum vacuum, the invisible energy field permeating all of space, and you've got the unsettling premise of vacuum decay. At its core, this isn't just another doomsday scenario. It's a cosmic game of Jenga where the wrong quantum fluctuation could pull the block that collapses everything. The rules of physics as we know them, the constants holding atoms together, even the speed of light itself might not be fixed features of reality, but temporary conditions in a universe that could, at any moment, rewrite its own operating system. The math behind this is as elegant as it is terrifying. Quantum field theory suggests our vacuum isn't in its true lowest energy state, but trapped in a false vacuum, like a marble resting in a shallow dent atop a hill, not the valley below. Given enough time, quantum tunneling could knock that marble into the deeper valley, triggering a bubble of true vacuum where the laws of physics are fundamentally different. This bubble would expand at the speed of light, its walls rewriting reality as they pass. One moment, stars shine and particles interact as usual. The next, the very fabric of causality unravels. The transition wouldn't just destroy matter, It would erase the rules that allow matter to exist in the first place. Critics argue this is speculative melodrama. The universe has persisted for 13.8 billion years without decaying. Why worry now? But supporters counter that absence of evidence isn't evidence of absence. Vacuum decay could be a 1 in a trillion years event, making our cosmic neighborhood stability a statistical fluke. Some models even suggest high-energy particle collisions could catalyze the transition, though experiments at the Large Hadron Collider have found no signs of such peril. The debate crystallizes a deeper philosophical rift. Is the universe inherently stable, or is our existence perpetually balanced on a knife's edge? The implications ripple beyond physics. If vacuum decay is possible, then every law we consider immutable, gravity, electromagnetism, even the structure of time, might be local bylaws in a grander cosmic scheme. It's like discovering your hometown's laws aren't federal mandates but municipal quirks that could be overturned by a distant legislature. This doesn't just challenge our sense of permanence, it redefines what reality even means. Are the constants of nature truly constant, or just the current settings in a multiverse where other bubbles operate with entirely different rulebooks? Yet the most haunting question isn't whether vacuum decay could happen, it's whether we'd see it coming. The bubble's expansion at light speed would grant no warning. 1 nanosecond, everything's normal. The next, the wavefront arrives and the concept of normal ceases to have meaning. In this scenario, the universe wouldn't end with fire or ice, but with a silent, invisible reprogramming of existence itself. Whether this makes the cosmos feel more precious or precarious depends on perspective, but one thing's certain: the ground beneath our feet and the stars above might be far less solid than they appear. Look up at the night sky and you'll see pinpricks of light stars, galaxies, the scattered jewels of the cosmos. Zoom out far enough, though, and those specks resolve into something eerily familiar. A vast, interconnected web of luminous filaments stretching across the void, with galaxies clustered like beads on invisible strings. This is the cosmic web, the universe's large-scale structure, and it bears an uncanny resemblance to another intricate network, the human brain. Side by side, images of neural pathways and galactic filaments could almost be mistaken for one another. The similarities don't stop at appearance. Both systems organize matter efficiently, minimizing connection lengths while maximizing information transfer. Neurons communicate via electrical impulses. Galaxies interact through gravity. The parallels are so striking that they've sparked a provocative question. Could the cosmic web be more than just a pretty pattern? Could it, in some way, be alive? At first glance, the idea seems like pure poetic fancy until you dig into the numbers. Take the Bolshoi simulation, a supercomputer model of the universe's growth. When researchers compared its galactic filaments to neural networks, they found both systems shared nearly identical clustering patterns. The universe's filaments even follow a mathematical principle called Zipf's law, which describes how frequently words appear in language, another system built for information. Then there's dark matter, the invisible scaffold shaping the cosmic web. Its distribution mirrors the brain's synaptic organization, with dense nodes linked by delicate threads. Of course, resemblance isn't causation. But when structures evolve similar architectures across wildly different scales, it's worth asking, is this just a cosmic coincidence, or could there be deeper principles at work? The debate hinges on a thornier question: what does it mean to be alive? Biology defines life by traits like growth, reproduction, and metabolism, none of which seem to apply to galaxy clusters. But what if we're thinking too small? Complex systems theorists argue that life might not require carbon or water, just the right organization of energy and information. From this perspective, the cosmic web could be a slow, cold form of life. Its metabolism, the gravitational dance of dark matter. Its thoughts, the ebb and flow of cosmic voids over billions of years. Philosopher Karl Popper once mused that the universe might possess a kind of plastic control, self-regulating like an organism. Could the cosmic web be the physical manifestation of that idea? Skeptics roll their eyes at what they call cosmic anthropomorphism, the human tendency to project our traits onto the universe. Astrophysicist Neil deGrasse Tyson dismisses the comparison as pattern recognition run amok. After all, lightning forks like a tree root and river deltas branch like lungs. That doesn't mean storms breathe or waterways photosynthesize. Critics argue the cosmic web structure emerges inevitably from gravity and dark matter, no more alive than a snowflake's crystal lattice. Yet proponents counter that dismissing the analogy outright misses a chance to rethink life's boundaries. If life is fundamentally about processing information, then the universe, with its quantum entanglement and gravitational feedback loops, might be doing just that on scales and time spans we can barely fathom. The most tantalizing clue lies in black holes. These cosmic engines don't just devour matter, they radiate energy, influence galactic evolution, and might even encode information on their event horizons, a holographic memory. String theorist Brian Greene speculates that black holes could function as nodes in a vast computational network, with the cosmic web as its circuitry. It's a staggering thought. The universe might not just contain information, but process it, with galaxies as transistors in a slow, cold computer the size of existence itself. Yet the hardest question isn't whether the cosmic web is alive. It's whether we'd even recognize cosmic life if we saw it. Our definitions are hopelessly Earth-centric, built around water, DNA, and rapid chemical reactions. But life on a galactic scale would operate at temperatures near absolute zero, over time spans longer than Earth's history, using gravity and dark energy as its tools. To such a system, a human lifespan would blink by faster than a quantum fluctuation. Perhaps the truth lies between extremes. The cosmic web may not be alive in any biological sense, but its structure could hint at universal principles that shape both neurons and galaxies, a deep mathematical unity underlying complexity at every scale. Whether that makes the universe a thinking entity or just a beautiful pattern depends less on physics than on how boldly we're willing to redefine what thinking even means. After all, if the cosmos can sculpt something as wondrous as a conscious mind, who's to say it isn't, in some way, conscious itself? Quantum tunneling is one of physics' most elegant sleights of hand. A subatomic magic trick where particles vanish through barriers they shouldn't be able to cross. Picture a ball rolling toward a hill. In classical physics, it needs enough energy to crest the top. But in the quantum realm, there's always a chance the ball will simply appear on the other side without climbing, as if the hill had a hidden tunnel. This isn't theoretical fantasy. We've measured it in labs, electrons teleporting through solid walls, protons fusing in stars at energies far too low for classical physics to allow. Now stretch this phenomenon back to the universe's first moments, and you arrive at a radical possibility. What if the Big Bang itself was the ultimate quantum tunnel, a cosmic Houdini act where reality slipped into existence by dodging the rules? The math is startlingly plausible. Quantum field theory describes the early universe as a seething foam of potential, where energy barriers separate nothing from something. Under normal circumstances, crossing that barrier would require unimaginable energy, like a car needing to accelerate to light speed to climb a curb. But quantum mechanics permits an escape clause. Given enough time, even the most improbable events become inevitable. In this light, the Big Bang might not have been a violent explosion, but a quiet probabilistic leap, a fluctuation in the quantum vacuum that, against all odds, tunneled into stability. It's as if the universe rolled cosmic dice for eternity until landing a perfect hand, bypassing the need for a traditional cause altogether. Critics pounce on the improbability. The odds of our universe tunneling into existence are so vanishingly small that invoking them feels like explaining a house's construction by suggesting a tornado assembled it from scattered lumber. Yet here's the twist: in an infinite or near-infinite quantum landscape, even the rarest events must happen eventually. String theorist Leonard Susskind frames this as the anthropic casino, a multiverse where countless universes flicker in and out of existence, with only the stable ones lasting long enough to host observers like us. The debate isn't just about physics, it's about whether we live in a meticulously engineered cosmos or the one in a trillion jackpot winner. The implications rattle philosophy's cage. If creation was a quantum accident, does that negate the need for a first cause? Theologians argue that quantum tunneling merely describes how the universe emerged, not why quantum laws permit such loopholes in the first place. Atheists counter that invoking a creator to explain the Big Bang now seems as unnecessary as blaming lightning bolts on Zeus. What need is there for divine intervention when probability and physics can do the job? The tension here isn't just academic, it reshapes how we view existence's fragility. A universe born from tunneling hangs by a thread of statistics, balanced between infinite nothingness and everything. Experiments might settle the score. If traces of primordial quantum fluctuations imprint on gravitational waves from the Big Bang's aftermath, future observatories like the Laser Interferometer Space Antenna LISA could detect them. Others hunt for bubble universes in cosmic microwave background anomalies, bruises from neighboring realities where tunneling events spawned separate cosmos. Until then, the theory remains a tantalizing what if, reminding us that the universe's origin might be stranger than any creation myth, a cosmic roll of the dice where the house odds were unimaginably long, but someone, somewhere had to win. What if every particle in our universe has a cosmic doppelganger living in a mirror reality where time runs backward? The idea isn't science fiction, it's rooted in one of physics' most robust principles, CPT symmetry. This fundamental rule states that if you take any physical system and flip its charge c, mirror its spatial coordinates p, and reverse the flow of time t, the laws of physics remain unchanged. In other words, a backward-running, left-handed antimatter universe would obey the exact same rules as ours. The math is airtight, but could such a twin cosmos actually exist? And if so, would it be a parallel reality or our own past? Picture a film reel of the universe playing in reverse. Stars absorb light instead of emitting it. Shattered cups leap from the floor to reassemble on tables, and people grow younger with each passing day. Now imagine that reel isn't just a thought experiment, but a real domain, born from the same Big Bang as ours but governed by inverted time. Nobel laureate Richard Feynman once proposed that antimatter might literally be ordinary matter moving backward through time. A single electron zigzagging through time could explain all electrons and positrons in existence. Expand that idea to an entire universe, and suddenly CPT symmetry isn't just an equation, it's a blueprint for a hidden cosmic twin. The implications send shivers down the spine. If a CPT mirror universe exists, it would share our origin point, the Big Bang, but evolve in the opposite temporal direction. From our perspective, their Big Bang would lie in our distant future, while our cosmic end might mark their dawn. Communication would be impossible, not just because of the temporal chasm, but because any signal we sent would be scrambled by the charge and parity inversions separating our realities. It's like trying to shout across a canyon where sound waves invert into silence the moment they leave your lips, yet skeptics raise formidable objections. Why don't we see evidence of this mirror cosmos? If the universe's expansion accelerates indefinitely, as dark energy suggests, a future Big Bang seems impossible. There'd be no contraction to recycle spacetime. Others argue that while CPT symmetry holds for particle interactions, applying it to the entire universe is a leap beyond empirical validation. The cosmic microwave background shows no signs of a temporal mirror image, no faint echo of a reverse universe brushing against ours. The debate takes a philosophical turn when we ask, what would time flowing backward even mean for conscious beings in that reality? Would they remember the future and anticipate the past? Physicist Sean Carroll suggests their experience might be indistinguishable from ours. Their perception of time's arrow could align with entropy's increase in their reference frame, making their past just as fixed and unchangeable as ours feels. This flips the script on free will. If both universes are equally real, does that render our choices predetermined from their perspective? Perhaps the most tantalizing clue comes from neutrinos. These ghostly particles violate parity symmetry. They spin like left-handed screws with no right-handed counterparts in nature. Some theorists speculate this asymmetry could be a fingerprint of a CPT-mirrored universe balancing the scales. If true, the universe might not just have a twin, it might need one to satisfy the deeper symmetries underpinning reality. While evidence remains elusive, the mere possibility reshapes how we view existence. A CPT mirror universe wouldn't just be another realm, it would be the ultimate cosmic complement, a yin to our yang, woven into the same space-time fabric, yet forever separated by the unbridgeable gulf of time's arrow. Whether it's out there or not, the theory forces us to confront a humbling truth. The universe might be far stranger and far more symmetrical than our limited perception can fathom. Gravity feels like the universe's most inescapable force, the silent hand that guides planets, bends light, and pins us to the ground. But what if this power isn't fundamental at all? What if it's just a side effect, an illusion emerging from deeper, more primal processes playing out at the smallest scales of reality? This radical idea turns Einstein's geometric masterpiece, general relativity, on its head, suggesting gravity isn't woven into spacetime's fabric, but arises from something far stranger, the chaotic dance of entropy. Picture a glass of water filled with ice cubes. As the ice melts, the water molecules grow more disordered, increasing the system's entropy, a measure of chaos. Now imagine spacetime itself behaves like that water, with tiny, invisible atoms of space flickering in and out of existence at the Planck scale. Theoretical physicist Eric Verland proposes that gravity might simply be the universe's way of maximizing entropy, a statistical tendency for these microscopic building blocks to arrange themselves in ways that create what we perceive as gravitational attraction. It's as if the pull you feel toward Earth isn't due to curved spacetime, but trillions of microscopic adjustments in the background noise of reality, all pushing matter together like driftwood clustering on a turbulent sea. The math behind this idea, dubbed emergent gravity, draws inspiration from black hole thermodynamics. When Jacob Bekenstein and Stephen Hawking discovered that black holes have entropy proportional to their surface area, it hinted at something profound. Gravity and thermodynamics might be two sides of the same coin. Verland's equations take this further, showing how entropy gradients, differences in disorder across space, could mathematically reproduce Newton's law of gravitation. and even Einstein's field equations without invoking gravity as a fundamental force. The implications are staggering. If gravity emerges from entropy, then dark matter, the invisible mass we've been hunting for decades, might not be a particle at all, but a mismatch between our outdated gravitational math and the universe's true statistical mechanics. Critics, however, aren't convinced. General relativity has passed every experimental test for over a century, from Mercury's wobbling orbit to gravitational waves rippling through spacetime. Why abandon a flawless theory for an unproven alternative? Skeptics like physicist Lee Smolin argue that entropic gravity lacks predictive power. It can't yet explain phenomena like the gravitational lensing of galaxy clusters better than dark matter models. Others point out that entropy-based theories struggle to reconcile with quantum mechanics, leaving us with a patchwork of ideas rather than a unified framework. Yet the debate isn't just about equations, it's about how we define fundamental. If gravity emerges, what else might be secondary? Electromagnetism. The nuclear forces. Some theorists speculate even time itself could be an emergent property, a collective illusion born from quantum entanglement. This perspective flips our understanding of reality. Instead of a universe built from immutable laws, we might inhabit a cosmic simulation running on statistical rules, where what we call physics is just the macro-level output of microscopic chaos. The most tantalizing clue lies in the holographic principle, the idea that our three-dimensional reality could be a projection from a two-dimensional boundary. If true, then gravity's emergence would make perfect sense. A force that leaks into our world from a lower dimensional code, like shadows cast by objects outside a cave. Experiments like the holometer at Fermilab are already hunting for signs of this pixelated spacetime, searching for quantum jitter in the fabric of reality that could betray gravity's true origins. Whether entropic gravity holds up or crumbles under scrutiny, it forces us to confront a humbling possibility. The forces we've long considered the bedrock of existence might just be surface ripples on a deeper, darker ocean of unseen principles. If gravity can emerge from chaos, then the universe is far more fluid and far more mysterious than Einstein ever dreamed. Imagine a universe so young it hasn't even formed stars yet, a hot, dense soup of particles where gravity could knot itself into tiny, invisible traps. These would be primordial black holes, not born from collapsing stars like their cosmic cousins, but forged in the chaos of the Big Bang itself. Some might be as small as an atom, yet heavier than a mountain, lurking unseen in the dark between galaxies. Here's the tantalizing possibility. What if these ancient relics aren't just cosmic oddities, but the missing piece of the dark matter puzzle? For decades, scientists have chased particles like WIMP and actions to explain dark matter's gravitational grip. But primordial black holes offer a radical alternative, no new physics required. Their sheer mass would bend light and warp orbits just like dark matter does, yet they'd be nearly impossible to spot directly. Think of them as cosmic ghosts, invisible, silent, but casting long shadows across the universe. The math is seductively simple. If enough of these tiny black holes formed in the early universe, their combined gravity could perfectly explain why galaxies rotate faster than visible matter alone should allow. The idea isn't without merit. When LIGO detected gravitational waves from colliding black holes in 2015, some were surprisingly heavy, hinting at a population of black holes that didn't fit standard stellar formation models. Could these be primordial survivors? Supporters point to other clues, like unexplained microlensing events where stars briefly brighten as unseen objects pass in front. These flickers could be primordial black holes drifting through the Milky Way, subtly warping starlight like lenses made of pure gravity. Yet skeptics wield Occam's razor. If primordial black holes were abundant, why don't we see more evidence? Their collisions would release bursts of gamma rays, and their gravitational influence would disrupt delicate structures like dwarf galaxies. Astronomers have scoured the cosmos for these signatures and come up largely empty. There's also the problem of timing. For primordial black holes to form, the infant universe needed patches of matter dense enough to collapse instantly, a scenario requiring fine-tuned conditions that might stretch plausibility. The debate pivots on a deeper question: is dark matter one thing or many? Primordial black holes could coexist with other candidates, each contributing to the total mass in different ways. Some models suggest a cosmic dark sector, with multiple components like a shadowy ecosystem where black holes, exotic particles, and even unseen forces interact in ways we're only beginning to imagine. This wouldn't dissolve dark matter's mystery so much as complicate it further, revealing layers we hadn't dared to suspect. What makes this theory so compelling isn't just its elegance, but its audacity. It dares us to reconsider black holes not as destroyers, but as architects, silent builders of the cosmic web, whose gravity sculpted the universe while remaining forever hidden. Whether they're the sole answer or just one piece of the puzzle, primordial black holes remind us that sometimes the darkest secrets hide in the plainest sight. Every star that flickers out, every engine that sputters to stillness, whispers the same chilling prophecy: entropy always wins. The second law of thermodynamics decrees that disorder must increase, that energy disperses until nothing remains usable, a fate called heat death, where the universe becomes a vast, featureless graveyard of exhausted particles drifting in endless darkness. But what if this cosmic obituary is premature? Beneath the grim inevitability of entropy, another possibility pulses with quiet defiance: the idea that the universe might not end in cold oblivion, but fold back on itself in a fiery rebirth, an eternal cycle of death and resurrection written into the fabric of space-time. Consider the numbers. Entropy's victory seems mathematically assured. Given enough time, think trillions upon trillions of years, black holes will evaporate via Hawking radiation. Protons might decay, and even the last embers of stellar remnants will cool to absolute zero. The cosmos will reach maximum entropy, a state where no work can be done, no structure preserved. It's the ultimate equilibrium, where time itself becomes meaningless because nothing changes anymore. Yet this bleak forecast hinges on a critical assumption: that gravity, the architect of cosmic structure, can't fight back. Enter Roger Penrose's conformal cyclic cosmology, a vision where the universe's distant future becomes mathematically indistinguishable from its fiery beginning. In this model, heat death isn't the end but a reset button, a smoothing of spacetime so complete that it births a new Big Bang. Picture an endless hall of mirrors where each reflection is a fresh universe, its dawn scrubbed clean of the previous cycle's entropy. The evidence is tantalizingly indirect. Penrose points to anomalies in the cosmic microwave background, concentric rings of temperature variation he calls Hawking points, which he interprets as scars from colliding supermassive black holes in a prior eon. These echoes, if real, would be cosmic fingerprints of a universe that came before. Skeptics counter that these patterns could be statistical flukes or artifacts of data processing. After all, the universe is under no obligation to satisfy our hunger for symmetry, but the allure of cycles persists, partly because it resolves the entropy paradox. If time is infinite, why isn't our universe already heat dead? Cyclic models answer by making entropy local. Each cycle starts fresh, its low entropy inherited not from decay but from the geometry of rebirth. Yet the debate isn't just about equations, it's about narrative. Heat death tells a linear story with a definitive ending, a tragedy where the universe's brilliance fades to black. Cyclic cosmology offers an epic, a saga without finality where existence reinvents itself eternally. Philosophers have wrestled with these contrasting visions for millennia, from the Norse myth of Ragnarok to Hindu cosmology's repeating kalpas. Modern physics reframes the dichotomy not as mythology, but as a tension between gravity and thermodynamics, between the universe's structure and its chaos. The stakes couldn't be higher. If heat death is inevitable, then all meaning is fleeting. Every poem, every civilization, every black hole dissolves into the void. But if cycles prevail, then the universe is a phoenix, its ashes the seeds of new creation. Perhaps the truth lies in between, not heat, death, or rebirth, but a third path we've yet to imagine. Until then, the question lingers: is eternity an endless winter, or the space between a cosmic heartbeat? The answer may depend less on physics than on how boldly we dare to redefine what forever means. Think of the universe as a cosmic film reel. What if the smooth motion we perceive is just an illusion, stitched together from countless tiny jumps too small for us to notice? This is the radical idea behind quantum cosmology, where the building blocks of reality might not flow like a river, but tick forward like the second hand of a clock, pixel by pixel. At the smallest scales, particles don't glide, they vanish from one state and reappear in another without crossing the space in between. These quantum leaps aren't just atomic quirks, they could be the hidden scaffolding behind the largest structures in existence. Take galaxy clusters, those glittering metropolises of stars bound by gravity. Traditional models assume space and time are smooth, with matter flowing seamlessly under gravitational tides. But simulations based on quantum gravity suggest something stranger, that cosmic evolution might advance in discrete hops, like a cosmic flipbook where each page represents a tiny but fundamental unit of spacetime. In this view, galaxies didn't form along unbroken trajectories, but through a series of microscopic corrections, as if the universe itself were buffering into existence. The cosmic web's intricate filaments, then, might not be the product of continuous forces, but the echo of countless quantum decisions stacking up over billions of years. Critics argue this overcomplicates a system already well explained by classical physics. After all, Einstein's relativity beautifully describes gravity's smooth curvature, and quantum effects typically vanish at macroscopic scales. But supporters counter with an unsettling truth. We've never actually tested spacetime's smoothness at the universe's most extreme resolutions. The Planck length, a scale a trillion times smaller than an atom, is thought to be where smooth geometry shatters into quantum foam. If true, then every galaxy, every star, even your own hands, might be built atop a foundation of imperceptible jumps, like a hologram rendered in invisible pixels. The debate takes a philosophical turn when we ask, what does real even mean if continuity is an illusion? Our brains evolved to perceive smooth motion, a survival advantage when tracking predators or falling objects. But nature might operate differently under the hood. Consider early animation. Flip through individual frames fast enough, and the mind stitches them into fluid motion. Could the cosmos work the same way, with quantum jumps too rapid and tiny for any instrument to detect? Experiments like gravitational wave detectors might soon test this by hunting for anomalies in spacetime's texture, subtle glitches that betray its pixelated nature. The most tantalizing clue lies in the cosmic microwave background's faint irregularities. These primordial wrinkles, frozen in time from the universe's infancy, show patterns that some theorists argue resemble the statistical noise of quantum fluctuations. If confirmed, it would mean the largest structures we see today, superclusters stretching hundreds of millions of light years, were seeded by jumps smaller than a proton. This wouldn't just reshape cosmology, it would redefine our place in the universe. We're not sailing on a smooth cosmic river, but riding a cascade of quantum leaps, each one a reminder that reality's clock might tick in ways we're only beginning to hear. Black holes are cosmic enforcers, shrouding their deepest secrets behind the ultimate velvet rope, the event horizon. Once you cross that boundary, there's no coming back, no signal, no glimpse of the crushing singularity at its core. But what if that rule isn't absolute? Imagine a black hole stripped of its event horizon, its singularity laid bare for the universe to see. These hypothetical monsters are called naked singularities, points of infinite density with no curtain, no firewall, no cosmic etiquette to shield us from the raw chaos beneath. The math allows for them. Einstein's equations don't forbid their existence, but if they're out there, they wouldn't just defy our understanding of gravity, they'd smash it to pieces. Picture a spinning black hole, whirling so fast that the centrifugal force counteracts its own gravity. Under extreme conditions, the event horizon could stretch, thin, and eventually vanish like a soap bubble popping, leaving the singularity exposed. No longer hidden, it would dangle in space like a glitching pixel in reality's code, a place where density becomes infinite, where space-time curvature turns so sharp it punctures the fabric of the universe itself. The consequences would be catastrophic, and not just for astrophysics. Without an event horizon to contain it, the singularity's gravitational madness would spill outward, warping causality, bending light into paradoxes, and potentially rewriting the laws of physics in its vicinity. Time could loop, cause and effect might tangle. The universe, at least locally, would lose its mind. The debate over naked singularities isn't just academic, it's a battle for the soul of predictability. Physicist Roger Penrose proposed the Cosmic Censorship hypothesis, a kind of cosmic rulebook that insists nature abhors a naked singularity as much as it abhors a vacuum. In his view, the universe has a built-in censor, a mechanism, perhaps quantum, perhaps gravitational, that always ensures singularities stay clothed behind event horizons. It's a comforting idea. Without it, the deterministic universe Einstein envisioned could devolve into anarchy, where outcomes aren't just uncertain but fundamentally uncomputable. A single naked singularity could turn physics into performance art, where the rules change depending on where you stand. Yet the universe has a habit of defying our comfort zones. Simulations of collapsing stars and hyper-spinning black holes suggest that under the right conditions, censorship might fail. Some models in string theory and loop quantum gravity even posit that naked singularities could form naturally, if rarely, like cosmic mutations in the wild. And if they exist, they wouldn't just sit quietly. Their gravitational fields could act as portals, bending light into closed loops or spewing out unpredictable jets of energy. They might even serve as factories for exotic particles, or worse, time machines, where the distinction between past and future blurs into nonsense. Skeptics counter that absence of evidence is evidence of absence. If naked singularities are possible, why haven't we spotted one? The universe isn't shy about flaunting its extremes: quasars, magnetars, gamma-ray bursts. So where are the gravitational rogues breaking all the rules? Others argue that even if they formed, they'd self-destruct instantly, collapsing into a more polite black hole or dissolving in a burst of quantum radiation. But supporters fire back. Maybe we're looking for the wrong signatures. A naked singularity wouldn't announce itself with the usual black hole fanfare of accretion disks and Hawking radiation. Its telltale signs might be subtler anomalous gamma-ray flashes, twisted light patterns with no visible source, or regions of space where gravity seems to glitch. The most unsettling possibility isn't that naked singularities exist, it's what their existence would imply about reality's stability. If a singularity can stand exposed, then the laws of physics aren't just breakable, they're negotiable. Equations that hold true everywhere else could unravel in its presence, like a thread pulled from a sweater. The very idea forces us to confront whether the universe runs on unshakable principles or if, in its darkest corners, anything goes. Whether cosmic censorship holds or not, the debate cuts to the core of why we do physics at all. Are the laws of nature absolute, or are they just suggestions? The answer might lie not in equations, but in the void waiting for some brave or foolish observer to stare back. Time crystals sound like something ripped from a science fiction epic, structures that pulse and oscillate without any energy input, defying one of physics' most sacred principles, the arrow of time. Imagine a snowflake that doesn't just sit frozen in space, but one whose atomic arrangement rhythmically shifts back and forth, ticking like a clock without ever winding down. This isn't hypothetical. In 2017, researchers at the University of Maryland created the first time crystal using a chain of ytterbium atoms, coaxing them into a state of perpetual motion locked in a loop, immune to entropy's relentless pull. The implications ripple far beyond the lab. If time itself can crystallize, then our understanding of permanence, of how the universe sustains order, might be standing on shaky ground. At the heart of this mystery is symmetry breaking, a phenomenon where systems settle into patterns that don't mirror their underlying rules. Think of water freezing into ice. The molecules adopt a rigid lattice, breaking the liquid's uniform symmetry. Time crystals take this a step further, breaking time's symmetry by oscillating at a fixed rhythm even in their lowest energy state. It's as if a pendulum could swing forever without gravity or a push, simply because the universe allows it. Nobel laureate Frank Wilczek, who first theorized time crystals in 2012, envisioned them as cosmic metronomes, ticking through eternity without batteries or springs. The catch, they don't violate thermodynamics because they don't produce usable energy. They just dance in place, a perpetual motion machine that powers nothing but our fascination. Critics initially dismissed time crystals as mathematical curiosities, arguing they'd require impossible conditions to exist, yet experiments proved otherwise. Using lasers and magnetic fields, physicists have now created time crystals in everything from diamonds to superfluid helium. The real shock came when Google's quantum computer Sycamore simulated a time crystal that resisted decay, even when disturbed, like a bell that rings the same note no matter how you strike it. This robustness hints at something profound. Time crystals might be more than lab oddities. They could be a new phase of matter, as fundamental as solids or liquids, but with time itself woven into their structure. Now, stretch this idea to cosmic scales. What if the early universe birthed primordial time crystal structures that still tick today, hidden in the fabric of space-time? Some theorists speculate that dark matter, the universe's invisible scaffolding, could harbor time crystalline properties, its particles cycling through states in a slow, cosmic rhythm. Others propose that black holes might exhibit time crystal behavior at their event horizons, where gravity warps time into strange loops. Even the vacuum of space, seething with quantum fluctuations, could be studded with microscopic time crystals, pulsating silently beneath the notice of our instruments. The debate isn't just about physics, it's about philosophy. If time can crystallize, then permanence might be an illusion, a fleeting equilibrium in a universe that prefers cycles over stillness. Ancient cultures spoke of eternal return, the idea that history repeats itself in grand cycles. Time crystals offer a scientific echo, not just recurrence, but rhythm baked into reality's blueprint. The question isn't whether we'll find more time crystals, but whether we've been missing a deeper truth all along. that the universe doesn't just move through time, it might be built from it. Skeptics urge caution. Time crystals in labs are fragile, fleeting things, a far cry from the cosmic scale structures theorists dream of. And without evidence of natural time crystals in the wild, the idea remains speculative. But the mere possibility reshapes how we see clocks. For centuries, we've measured time by counting repetitions, the swing of a pendulum, the vibration of atoms. Time crystals suggest a radical alternative. What if time isn't something we measure, but something that measures itself? The answer could redefine not just our watches, but our place in a universe where even time has a heartbeat. We think of space as an endless, featureless stage, flat, predictable, and infinite. But what if the universe is playing tricks on our perception, bending in ways too subtle for our instruments to catch? The Planck satellite, our most precise cosmic cartographer, has mapped the universe's geometry with breathtaking accuracy, and the data points to a startling conclusion. Space appears perfectly flat, like an infinite sheet of paper stretching forever in all directions. Yet here's the twist. The measurements come with a razor-thin margin of error, a sliver of uncertainty that leaves just enough room for the cosmos to be subtly curved, like the surface of a sphere so vast its curvature eludes our notice. The difference between these two possibilities isn't just academic. It determines whether we live in a cosmos that goes on forever or one that loops back on itself like a cosmic Möbius strip. Picture standing in a field, gazing at the horizon. On a flat Earth, you'd expect to see forever, but if the planet were large enough, the curve would be imperceptible and the horizon would still look flat. The universe operates on a similar sleight of hand. If space has positive curvature, like a four-dimensional globe, traveling far enough in one direction would eventually bring you back to your starting point, like an ant crawling around a basketball. Negative curvature, though, would warp space into a saddle shape, a hyperbolic landscape where parallel lines diverge wildly, and triangles deface Euclidean geometry with angles summing to less than 180 degrees. Planck's data leans toward flatness, but the uncertainty is like a whisper at the edge of hearing. What if you're missing something? The stakes couldn't be higher. A flat universe implies infinite space, endless galaxies, and the eerie prospect of infinite copies of yourself scattered across the void. A closed, positively curved cosmos, though, would be finite but boundless, a cosmic Ouroboros where the last page of the story loops back to the first. The real mind bender. If the universe is curved, the scale of that curvature would dwarf anything we can observe. The radius of such a universe might be hundreds of times larger than the visible cosmos, making the curvature undetectable except through statistical ghosts in the data. Critics argue that flatness is the simplest answer, aligning with inflation theory's prediction that the early universe stretched space so violently it ironed out any primordial wrinkles. Yet skeptics counter that inflation doesn't require perfect flatness, just something very close. And if the universe is even slightly curved, it would upend our understanding of its ultimate fate. A closed universe might eventually collapse in a big crunch, while an open, negatively curved one would tear itself apart in a perpetual runaway expansion. The cosmic microwave background holds clues, with temperature fluctuations acting as a fingerprint of spacetime's shape. Those patterns mostly match flatness, but mostly isn't definitively. The debate takes a philosophical turn when we ask, what does flat even mean in a universe with dark energy stretching the fabric of reality? Could accelerating expansion disguise curvature over time, like a balloon inflating so fast its surface appears flat to a tiny ant? Some theorists propose that the universe's geometry might not be uniform, that we could be living in a local flat patch of a larger, warped cosmos, like a calm lagoon in a stormy ocean. The most tantalizing possibility isn't just about shape but connection. If the universe loops back on itself, could ancient light have circled the cosmos multiple times, creating faint echoes of the same galaxies in different patches of the sky? Astronomers have searched for these ghost images in the cosmic microwave background, the ultimate hall of mirrors. So far, nothing conclusive, but the hunt continues. Whether flat, curved, or something stranger, the geometry of the universe isn't just a mathematical abstraction. It's the bedrock of reality itself, the hidden scaffolding that dictates everything from gravity's grip to the destiny of all existence. The answer won't just reshape our maps of the cosmos, it will redefine what infinity even means. Chaos and destruction seem like the antithesis of creation, yet look closely at the universe's grand design, and you'll find fingerprints of violence everywhere. The cosmic web's intricate filaments, the vast voids between galaxies, even the distribution of matter itself might trace back to primordial turbulence, a storm of quantum chaos in the universe's first moments. Picture the Big Bang not as a smooth expansion, but as a seething cauldron of fluctuations where space itself rippled with violent energy. These weren't just random wrinkles, they were the seeds of everything. When physicists analyze the cosmic microwave background, they're essentially reading the aftershocks of those early quakes, hotspots and cold spots that eventually grew into galaxies and voids. It's as if the universe's blueprint was drawn in the aftermath of a quantum earthquake, with every tremor shaping the destiny of matter. But how does chaos birth order? Think of a pot of boiling water. At first glance, it's pure disorder, bubbles forming and bursting at random. Yet beneath the surface, there's a hidden pattern, convection currents, where heat and motion create structured flows. The early universe might have worked the same way. Quantum fluctuations, tiny, violent jumps in energy, could have acted like microscopic bubbles, their randomness amplifying over time into the large-scale structure we see today. Simulations show that without these initial disturbances, matter would have spread too evenly, leaving no gravitational footholds for galaxies to cluster. Destruction, in this light, isn't the enemy of creation, it's the chisel that sculpted the cosmos. The implications rattle our intuition. If chaos is a creative force, then the voids between galaxies aren't empty failures, they're the negative space of a masterpiece, carved out by the same turbulence that piled matter into stars. Even black holes, those infamous destroyers, might play a role in this delicate balance. Some theories suggest their violent mergers in the early universe could have stirred the cosmic pot, redistributing matter in ways that encouraged galaxy formation. It's a paradox worthy of ancient myth. The universe's architects are also its wrecking balls. Skeptics push back, arguing that turbulence alone can't explain the precision of the cosmic web. Why do filaments align so perfectly? Why do voids have such crisp edges? Alternative theories propose hidden forces, dark matter's invisible scaffolding, or primordial magnetic fields, acting as cosmic shepherds, guiding chaos into order. Yet even these models concede that without that initial quantum violence, the universe would lack its defining texture. The debate isn't about whether chaos played a role, but how much credit it deserves. Perhaps the most profound takeaway isn't scientific but philosophical. If destruction can be creative, then the universe isn't a static monument. It's a dynamic dance of creation and dissolution, where every ending feeds a new beginning. Supernova forge the heavy elements of life. Galactic collisions spark star birth. Even entropy's march toward disorder fuels the engine of change. The cosmos doesn't just tolerate chaos, it thrives on it. Far from a flaw in the design, violence might be the very mechanism that made existence possible. Whether this harmony in discord is a happy accident or a fundamental law, one thing's certain: the universe's most beautiful structures were born from its fiercest storms. If our universe began with a big bang, what's stopping countless others from doing the same? The theory of eternal inflation paints a dizzying picture, a cosmic froth where new universes bubble into existence endlessly, each with its own laws of physics, its own version of time, its own destiny. Picture an infinite ocean where every wave crest is a big bang and every trough a separate reality. But here's the catch. These sibling universes aren't just far away, they're fundamentally unreachable, hidden behind horizons where space stretches faster than light can traverse. If we can't see them, can't touch them, how do we know they're not just mathematical fantasies? The idea hinges on inflation, the theory that our universe underwent a hyper-fast expansion in its first moments. But what if that expansion never truly stopped? What if pockets of space-time keep inflating eternally, birthing new universes like buds on a cosmic vine? The math suggests it's possible. Quantum fluctuations in the inflating field could trigger localized pinch-offs, creating self-contained bubbles of space-time that evolve independently. Some might collapse instantly, others could spawn galaxies, stars, even life. The problem: once a bubble universe forms, the space between it and its neighbors inflates so rapidly that no signal, no particle, no force could ever bridge the gap. They're islands forever adrift in an ever-widening sea. Critics argue this makes the theory untestable, a textbook example of not even wrong. If other big bangs leave no trace in our cosmos, isn't invoking them just storytelling? Not necessarily. Some physicists hunt for indirect clues, like bruises in the cosmic microwave background where our universe might have grazed another bubble long ago. Others suggest that the universe's startlingly low entropy, its inexplicable orderliness at the Big Bang, could be a fossil of a larger multiverse, a natural outcome of eternal inflation's statistical whims. It's like finding a perfectly stacked deck of cards and inferring the existence of countless other shuffled decks elsewhere. The debate isn't just about cosmology, it's about the limits of knowledge. If reality contains realms forever beyond observation, does science have to accommodate them or dismiss them as metaphysics? Some argue that unobservable universes are no different from unobservable dimensions in string theory, speculative, but mathematically coherent. Others counter that science demands falsifiability, and eternal inflation risks drifting into anything-goes territory. Yet even skeptics admit the theory's elegance. It explains why our universe's constants seem finely tuned for life. If every possible combination exists somewhere, we'd naturally find ourselves in a habitable corner. The most tantalizing possibility isn't just that other Big Bangs happened, it's that they're happening right now in a rhythm without beginning or end. Whether we'll ever find proof remains uncertain, but the mere idea reshapes how we see our place in existence, not as the center of creation, but as one spark in an infinite cosmic bonfire, burning with mysteries we may never reach. Imagine a universe where reality doesn't solidify until someone looks at it, where particles hover in ghostly superposition until consciousness steps in to decide their fate. This isn't the plot of a sci-fi novel. It's the spine-tingling premise of the von Neumann-Wigner interpretation, a fringe but mathematically coherent view of quantum mechanics that places observers' human minds at the center of existence. At its core, this idea flips the traditional script. Instead of the universe unfolding impersonally, governed by cold equations, it suggests that consciousness itself might be the sculptor, chiseling certainty from quantum fog. The implications are staggering. If true, the cosmos isn't just observed, it's defined by observation, with every measurement not just recording reality, but actively creating it. The roots of this debate trace back to the infamous double-slit experiment, where particles behave as waves when unobserved but snap into definite positions the moment they're measured. Mainstream physics explains this through decoherence environmental interactions collapsing wave functions. But von Neumann and Wigner dared to ask, what if the ultimate environment is the observer's mind? Their math treats consciousness as a non-physical entity, a singularity outside the quantum system that forces probabilities to crystallize. Picture a cosmic game of 20 questions where the answers don't exist until someone asks, except here, the questions are experiments and the questioner is you. Critics pounce on the slippery slope this creates. If consciousness collapses wave functions, where do we draw the line? Does a cat's observation count? A bacterium's, the interpretation's proponents argue that only self-aware minds qualify, drawing a sharp boundary at human or perhaps advanced AI cognition. But this raises thorny questions about panpsychism, the idea that consciousness is universal, with even particles possessing rudimentary awareness. Some theorists, like quantum physicist Henry Stapp, sidestep this by proposing that consciousness isn't creating reality but selecting it from a menu of quantum possibilities, like a diner choosing from a cosmic buffet. The debate spills into cosmology when we ask, what observed the Big Bang? If consciousness is required to collapse quantum states, how did the early universe transition from probability to fact without observers? One radical solution, retrocausality. The universe's wave function might have collapsed backward in time when the first conscious beings emerged, like a ripple flowing upstream to its source. Others suggest a cosmic consciousness, a primordial observer embedded in the fabric of reality itself. Philosopher Bernardo Kastrup takes this further, framing the universe as a collective dream, where individual minds are dissociated fragments of a single, universal awareness. Yet skeptics wield Occam's razor. Why invoke consciousness when decoherence explains wave function collapse mechanically? Experiments with quantum dots show superpositions collapsing without conscious observers, just through interactions with their environment. Nobel laureate Steven Weinberg dismissed the von Neumann-Wigner view as mysticism smuggled into physics, arguing that it conflates the map with the territory, the act of measurement with the measurer's mind. The most unsettling implication isn't about particles, it's about agency. If consciousness shapes reality, do our thoughts ripple through the quantum field? Studies like the Global Consciousness Project claim to detect statistical anomalies in random number generators during global events, as if collective attention bends probability. The scientific consensus dismisses these as noise, but the allure persists. What if prayer, intention, or even anxiety subtly warp the fabric of existence? Whether the von Neumann-Wigner interpretation holds or crumbles, it forces us to confront a humbling possibility. The universe might not be a cold, indifferent machine, but a participatory drama where mind and matter dance inseparably. The answer won't just redefine physics, it could rewrite what it means to be. After all, if observation creates reality, then the greatest cosmic mystery might not be out in the stars, but in the mirror. Numbers don't just describe the universe, they might be the universe. Think about the uncanny precision of a sunflower spiral, where each seed aligns at exactly 137.5 degrees from its neighbor, following the Fibonacci sequence with flawless accuracy. Or consider gravitational waves, ripples in space-time predicted by Einstein's equations decades before we detected them. These aren't just happy coincidences, they're clues that reality runs on an invisible code, a mathematical framework so precise it feels less like a tool we invented and more like a buried treasure we're slowly uncovering. This idea isn't new. Pythagoras believed numbers were divine, the hidden language of the cosmos. Galileo declared the universe a grand book written in mathematical symbols. But here's where the debate ignites. If math is the universe's operating system, does that mean we're discovering eternal truths, or just inventing a system that happens to fit? Take imaginary numbers, for example. Once dismissed as a quirky thought experiment, they're now essential for quantum mechanics and electrical engineering. Were they always part of reality's blueprint, waiting for us to stumble upon them? Or did we create a tool so adaptable it could latch onto deeper patterns we don't yet understand? Critics argue math is a human construct, a refined extension of our innate pattern-seeking instincts. After all, different civilizations developed distinct mathematical systems. Babylonians used base 60, while the Maya had a concept of zero long before Europe. If math were universal, wouldn't all cultures have converged on the same rules? Yet supporters counter with the unreasonable effectiveness of mathematics, a phrase coined by physicist Eugene Wigner. How is it that abstract equations concocted purely in human minds can predict the behavior of subatomic particles or the orbits of planets with staggering accuracy? It's as if we're cracking a cosmic cipher, one theorem at a time. The tension sharpens when we examine physics' greatest theories. General relativity bends spacetime with the elegance of a geometric proof. Quantum mechanics dances to the tune of probability amplitudes, complex numbers that somehow map onto real-world probabilities. String theory imagines particles as vibrating strings, their harmonies dictated by 10-dimensional math. Are these just metaphors, or is the universe literally made of mathematics? Max Tegmark's mathematical universe hypothesis takes this to the extreme, proposing that reality isn't just described by math, it is math, an abstract structure we're embedded in like characters in a cosmic equation. Yet the skeptics aren't convinced. If math is the universe's true language, why does it sometimes fail? Dark matter and dark energy resist tidy mathematical descriptions, leaving physicists scrambling for new frameworks. Chaos theory shows how deterministic equations can spawn unpredictability, reminding us that even perfect math might not guarantee perfect prediction. And then there's Gödel's incompleteness theorems, which prove that even within mathematical systems, there are truths that can't be derived from their own rules. Does this mean reality has built-in mysteries even math can't penetrate? Perhaps the answer lies in between. Maybe math isn't the universe's native tongue, but a Rosetta Stone, a translation manual that lets us decode reality's deeper patterns without fully grasping their essence. Like a flashlight in a vast cave, it illuminates patches of truth while leaving the larger structure shrouded. Or maybe we're asking the wrong question altogether. Instead of debating whether math is discovered or invented, we should marvel that our minds can engage with the cosmos in such profound ways, whether by uncovering eternal truths or crafting tools so powerful they blur the line between invention and revelation. One thing's certain, every time a mathematical prediction aligns with experimental data, every time an equation unlocks a new technology or reveals a hidden cosmic law, we're witnessing something miraculous. Whether it's the universe whispering its secrets or our minds projecting order onto chaos, the conversation itself proves one undeniable truth: mathematics, real or invented, is the closest thing we have to magic. Quantum supremacy, the moment when a quantum computer outperforms the best classical supercomputers, feels like a triumph of human ingenuity. But what if it's also a cosmic clue? Imagine a quantum machine so powerful it could simulate entire universes, atom by atom, law by law. Now ask yourself, if we're on the brink of creating such simulations, how do we know we're not already inside one? This isn't just speculative futurism. It's a debate that bridges quantum physics and metaphysics, forcing us to confront whether complexity itself might be the signature of a deeper cosmic code. The idea gains traction when you consider how quantum computers work. Unlike classical bits, which are either 0 or 1, qubits exist in superpositions multiple states at once. This lets them explore countless possibilities simultaneously, solving problems that would take classical machines millennia in mere seconds. Now scale that up. A sufficiently advanced quantum system could, in theory, simulate not just molecules or weather patterns, but the fundamental physics of a universe. If that's possible, then the sheer complexity of our own cosmos, with its fine-tuned constants and intricate laws, starts to feel suspiciously like the output of an unfathomably advanced computation. Supporters of the simulation argument, like philosopher Nick Bostrom, frame this as a statistical inevitability. If civilizations eventually develop quantum simulation technology, and if they choose to run ancestor simulations, digital recreations of their past, then the number of simulated minds would dwarf the number of biological ones. Odds are we'd be among the simulations. Physicist Seth Lloyd takes it further, suggesting that the universe might literally be a quantum computer, with every particle interaction performing a calculation. In this view, the Big Bang wasn't just an explosion of energy, it was the booting up of a cosmic operating system. Yet skeptics push back hard. For one, quantum simulations have limits. Even with qubits, simulating every particle in our universe would require more resources than the universe itself contains, a paradox that seems to rule out nested simulations. Then there's the problem of the substrate. If our reality is a simulation, what's running it? Another universe with different physics. At some point, you hit a base layer of reality that can't be simulated, or the chain becomes infinite. Nobel laureate Frank Wilczek argues that the universe's mathematical elegance suggests it's the real deal, not a construct. The debate takes a philosophical turn when we ask, what would cosmic code even look like? In our own simulations, we program rules: gravity, electromagnetism, the speed of light. But in a quantum simulation, the rules might be more fluid, with probabilities and superpositions baked into the framework. Some theorists point to quantum indeterminacy as potential evidence. The fact that particles don't settle into definite states until observed could be read as a cosmic optimization strategy, like a video game rendering only what the player sees to save processing power. But here's the twist. If we're in a simulation, the programmers might have left bugs or Easter eggs. Physicists have scoured the cosmic microwave background for glitches, patterns that betray a pixelated universe. Others hunt for anomalies in high-energy particle collisions that might reveal rounding errors in the code. So far, nothing conclusive. Yet the absence of evidence isn't evidence of absence. A sufficiently advanced simulation would be indistinguishable from reality to its inhabitants. The most profound implication isn't about our potential artificiality, it's about meaning. If the universe is a quantum computation, then free will might be an illusion, our choices predetermined by algorithms. Alternatively, if consciousness is the mechanism that collapses quantum probabilities into reality, we might be co-authors of the simulation, our observations shaping the code as we go. The line between creator and creation blurs, leaving us with a haunting question. Are we the programmers, the programmed, or something stranger, a self-generating loop of cosmic consciousness? Whether quantum supremacy hints at simulation or not, it forces us to confront the unnerving possibility that reality might not be the bedrock we thought. The universe could be less like a machine and more like a language, its laws not fixed commandments but dynamic expressions of a deeper, more elusive syntax. And if that's true, the next great leap in physics might not be discovering new particles but deciphering the source code of existence itself. From the echoes of the Big Bang to the whispers of parallel worlds, these 42 cosmic debates reveal something extraordinary. Our universe isn't just expanding, it's alive with questions. Every theory we've explored, from the holographic principle to the simulation hypothesis, isn't just about distant galaxies or abstract equations. It's about us, how we fit into this grand puzzle, why we're here at all, and what it means to stare into the void and demand answers. Think about the sheer audacity of that. A species born on a speck of dust orbiting an unremarkable star has dared to map the birth of time itself, to question whether reality is a cosmic accident or an elaborate code. We've probed black holes for secrets, chased dark matter through the shadows, and wondered if the laws of physics are just local bylaws in a multiverse teeming with alternate realities. And here's the beautiful part, we're not done. Every answer unravels new mysteries, like peeling an infinite onion where each layer reveals deeper, stranger truths. Take the debate over cosmic fine-tuning, for example. The fact that we're here to ponder it at all feels like a miracle. Tweak the strength of gravity by a fraction, or nudge the cosmological constant, and stars wouldn't ignite, atoms wouldn't bond, and life as we know it would be impossible. Does that precision imply a designer, a multiverse where every possible configuration plays out? Or is it simply the universe's way of telling us there's more to the story? The questions themselves are gifts, invitations to keep searching, to stay restless, and let's not forget the wild cards, the ideas that stretch our imagination to the breaking point. If the universe is a hologram, are we just shadows cast from some distant, two-dimensional boundary? If time isn't fundamental but emergent, does that mean the past and future are equally real, frozen in a block of space-time where free will is an illusion? These aren't just thought experiments, they're doorways to new ways of seeing. They force us to confront the limits of our intuition, to admit that reality might be stranger than any fiction. Here's the real magic. This conversation isn't reserved for physicists in lab coats. It belongs to anyone who's ever looked up at the night sky and felt that tug of wonder. Maybe you're Team Multiverse, convinced there's a version of you out there who chose that job offer you declined. Or perhaps you're captivated by the idea that consciousness itself might be the key to quantum reality. Whatever resonates, remember, your curiosity is part of the equation. Every time someone questions, debates, or dreams up a new theory, the universe gets a little less mysterious. So, which of these 42 debates lights a fire in your mind? Drop your thoughts in the comments. Let's keep the conversation cosmic. And if you've enjoyed this journey through the edges of understanding, hit subscribe. Because one thing's certain, the universe isn't done revealing its secrets. The next breakthrough, the next aha moment could be just around the corner. Stay curious, stay bold, and most of all, keep looking up. The greatest story ever told is still being written, and you've got a